gehen.
Ah,
Da, genau.
ich dachte, ich hab's schon.
Und dann startet er, egal mit welcher Uhrzeit.
Gut, super. Ach so, ja, ich hatte eigentlich bloß nicht geklickt. Ja, super. Und es heißt, dass wenn ich hier das ändere, das sollte dann hier mal wieder.
Das ist jetzt halt ein bisschen verzögert, ne? Dauert halt einen Moment, ja.
Ah ja, genau. Aber wenn es einen Moment dauert, ist es vielleicht gut, weil dann kann ich. Das sollte. Ah ja, Webcam muss ich jetzt noch.
Aber hier sollten wir die Bildschirmfreigabe, oder? Ausschneiden. Da sollten wir nicht das ganze Zoom-Fenster.
Ich würde dann.
Und das war noch 2019, 2018 oder so.
Ach ja. What the fuck? What is that? Ah, so. So geht es dann, ne?
Aber dann haben wir immer noch die ganzen Zoom-Controls damit drin. Du kannst auch das OBS-Fenster einfach zuschneiden, oder?
Ja, stimmt. Weil immer, wenn ich rausgehe, kommt es dann irgendwie zurück, ne?
Ja, du musst im Vollbild bleiben. Und du kannst doch mit einfach hier deine Dings wechseln.
Ja, aber das mache ich nie so. Warte mal. Ja, ich habe ihn nur kurz gesehen. Hey.
Ja, auf jeden Fall eine tolle Ausstellung, da war ich jetzt gerade. Hi.
Hey.
Das ist aber sehr liebevoll, was du da machst. Passen die nicht rein? Aber jedenfalls schon.
Der eine Professor,
aber der. Ups.
bitte unbedingt.
Booklets liegen draußen.
Ja, auf dem Tisch liegen schon welche. Ich weiß ja, wo sind dann die anderen?
Die sind im. Wo ist der denn?
Sind die alle auf dem Wagen?
Ja.
Ich dachte, da wären jetzt nur die Bücher, die Print Architecture in den 2 Kisten.
Nee, ich glaube,
Das sind die Books.
das sind die beiden.
Wo sind die Bücher?
Warte mal, das musst du Philipp fragen. Ja, also ich mache jetzt das hier kurz fertig und dann prüfe ich. Danke, hey.
Mark ist weggelaufen.
Nein, nee, der Clark ist.
Oh, dann hätte er gesprochen. Wobei er kauft jetzt nicht extra was, sondern sammelt nur in der VIP-Lounge.
Nee, der kauft extra.
Oh Gott, nee, du weißt es.
Keine Ahnung, eigentlich sollte es den Screenshare von Mirko sein. Und das kommt von der Präsentation.
Julia.
Naja. Ich habe die Präsentation noch nicht ganz geguckt, die ich bekommen habe.
Haben wir irgendwo ein Programm, wann was stattfindet?
Im Booklet nicht.
Im Booklet nicht? Gibt es als Ausdruck oder?
Ich habe auch
Nein.
Nee,
mit
ne,
dem
und,
Ja, und wir haben das als Ausdruck
Vorne.
so vorne, aber das ist dann alles. Nee, weil das machen wir eigentlich nie.
Nö,
Da steht halt unten, steht dann Transparenz.
Ich habe mich eigentlich am Freitag ein bisschen gewundert, ob wir das versuchen, aber dann war es mit dem Drucker so verrückt, dass ich es dann nicht mehr gemacht habe.
irgendwie, ich meine, alle haben Mobile. Man muss auch nicht die Leute irgendwie.
Aber es ist die Frage, ob
Können wir es auf
irgendwas-
Instagram noch?
Genau, auf Instagram wollte ich es gerade posten und ob wir es noch irgendwo ausgedruckt bekommen vielleicht. Von den Messeleuten.
Sorry, ich prüfe.
Aber ich meine, es ist jetzt auf den Displays, ne? Und es ist im Formnext
Dann haben
Programm.
wir Social Media noch.
Ja, ich denke auch, das ist dann der Intelligenztest. Ob das so
Ja, also bevor ich.
Noch weniger gekommen.
genau.
Ja, unten.
Und Lydia ist aber erst am Nachmittag. Ah, ist doch super.
Ja, genau, sie hat mir geschrieben, sie kommt früh genug an, dass seine Session ist. Glücklicherweise haben wir Miriam und die Nora gewechselt. Miriam und die Nora haben wir gewechselt. Das passt nicht so gut zu den Sessions, aber Miriam ist eigentlich am Morgen nicht da. Und ich habe es letzte Woche erfahren.
Der Bruno, hast du von dem was gehört? Weil er ist nicht beim Dinner aufgetaucht.
Nee, ich habe Slides auch noch nicht bekommen. Ich habe eine E-Mail bekommen ein paar Tagen hier, dass alles wie normal stand. Ich prüfe jetzt kurz nur die Webcam.
Mach mal dein Zeug. Ich will dich gar nicht von der Arbeit abhalten.
Den Tisch bewegen, dass ich den Laptop damit ich den irgendwie nur da, dass ich den Laptop hier, ich weiß nicht wann.
Ja, wenn am Ende von der
Ja,
Bühne.
ich war neulich in Paris.
Hast du schon versucht zu streamen?
Ja, alles klar. Ich habe mit Philips Laptop geprüft. Er streamt jetzt eigentlich das hier gerade, das gleich anfängt.
Soll ich es mal ausprobieren? Oder habt ihr schon ausprobiert, ob man
Wir haben schon probiert, dass man es auf der YouTube-Seite sieht. Und ja, ich muss jetzt noch den Webcam einstellen, damit man den Speaker sieht. Und ich glaube, wir sind dann mit dem Stream völlig bereit. Ich würde dann nur kurz prüfen, dass es im Stream hier gut aussieht. Also ein paar Details.
Ja, und ich glaube, was interessant ist, was immer das Problem ist, ob bei Zoom und so, ob die Videos übertragen werden in die Streams. Also wenn wir ein Video auf der PowerPoint haben,
So, ja. Wir haben ein paar verschiedene Präsentationen, wir können das auch prüfen.
Wenn ich das Problem auch, dass das gleichzeitig läuft, dass es den.
Ach so, ja, dann ist es, aber es wird alles ein bisschen verzeugt. Das haben wir mal mit Philipp jetzt geguckt. Das dauert ja ein paar Sekunden bis.
Aber ihr habt diesen Zugang jetzt bekommen für das schnellere Internet?
Ja. streaming again. And then this is all set up. I checked that.
Can you double check the audience cam?
1 minute early. Thanks.
Of course. Can you move this?
Ja.
Echt? Hm.
Ob wir da jetzt kurzfristig was machen können. Oder in Philipp. Kurze Frage von Team Graz. Die sind nicht durch den Registrierungsprozess gegangen bei uns. Stehen jetzt am Eingang und fragen, können wir kurzfristig ein Projekt generieren?
Ja, mache ich gleich.
Können wir machen.
Mache ich sofort.
Das kommt bei euch an per E-Mail. Ja?
Genau,
Ein paar Minuten warten. Wir müssten 3-mal TU Graz da drin haben. Kannst du es vielleicht nach
Warte mal. Ich guck mal, wir haben hier eins.
Andreas Trummer, Georg Hansemann und wie war der dritte Name? Entschuldigung. Georg Hansemann, Andreas Trummer. Oh, ach so, ihr beide, okay. Ja, nee, das machen wir jetzt.
Gut,
ja?
das schicke ich jetzt.
Kommt gleich. Ciao.
Die haben das.
Kein Problem. Bis gleich.
Und Andreas dann auch noch.
Andreas Trummer.
Okay, ich mache das jetzt gleich für die beiden und dann wahrscheinlich noch ein paar andere Leute, die das gerade.
Ja, so. Mondfunde von Fuß und Potenz.
Zweite Etage. Gut, ich bin entspannt. Die anderen Menschen müssen üben. Schon berufen kann. Ja, gerne. Probiert aber mal zwischen. Habt ihr Kontrolle über die Runde? Ja. Also jetzt ist es noch angenehmer, aber ich glaube, dann wäre eine Präsentation.
Naja.
Ja, aber jetzt von der anderen Seite auch.
Do you need to test something?
I just want to log you into a different Wi-Fi.
Just give me 1
Take your
second.
time. There's a new login.
Gelaufen, ich habe dann irgendwo auf einer anderen Webseite schon gesehen.
Oh, you have to.
Oh, ja.
Reconnection successful. Hast du es probiert mit anderem Lederhaltung?
Geht's los? Jetzt gleich?
You don't have any other slides for our opening, do you?
No.
And
Do you have some?
I have some just for the book, for one of the book announcements.
But do you want to do it at the beginning? Yeah.
Because it's kind of our only speaking slot. I think
Yeah.
Lee and Oliver can just show it again later.
Yeah. So it's this one, right? And then it's already in the...
Yes.
Okay,
Yeah,
good.
Mirko already has it.
So how do you want to start with the book or finish?
Finish our announcement with the book.
Okay.
I would say we just open the day. Let them know that we need the PhD titles on the list, so if they have them, put them in there. We have catering here, free to take for everyone anytime. Maybe you introduce the 3 sessions real quick.
Yeah.
We have 3 sessions, 3 moderators, a couple of presentations each, and a lunch break. Everything will be streamed, so we'll pass around the microphone if you ask questions.
Yeah. And then that's it. So we mostly do practicalities.
When you set up the speakers at the thing, let them know that they're supposed to be 10 to 15 centimeters away from the microphone. That's what the audio guy told me. I'll let Mirko know too, because he...
Yeah. Yep. Hi. Okay, Tiffany is on her way now. I think she's like figuring out how to get here, and she's our first moderator. So
Gut, Sie. Ins Symposium. Alle Kabel sind alle geregelt. Danke dir. Genau, bis gleich.
Ich war noch nicht da, ich habe auch von Sie gesendet.
Yeah, so we have a few more things. Okay, I can also, I'll put mine as well. Yeah, it's in, it would be in there. Mirko can show you. Mirko, can you show Tiffany where to put her presentation slides on your
Yeah.
computer? Yeah.
We start. Maybe we wait a couple more.
Yeah.
Just give me 1 second and then I will give it to you.
No. Oh, that's nice. What is it? Ah, it's easy.
I have one, but maybe
Let's keep it around. And then,
Here in my
yeah,
email there anyway.
we just need Andreas' presentation. And then
They had trouble getting in.
I will.
Wo soll es jetzt hin?
Eigentlich hier rein. Das war uns Slot frei. Ist es C oder?
C.
Haben wir noch einen C-Slot?
Ja, verdammt.
Ah, warte. Sollen wir die Präsentation direkt auf deinen Rechner machen? Das ist schlauer, oder?
Ja.
This one wasn't either. That's why we're saying that.
Good morning, everyone. Can I ask you to slowly take your seats so we can start?
Okay, hi everyone, welcome to week 2023 Built Environment Additive Manufacturing. We are very happy to welcome you to this year's edition. I have a few things to tell you before the first session starts. First of all, we apologize for the slight delay in technicalities in starting, but we're now ready. Maybe a very brief input into what we will listen today. It's customary at Beam to say that every year we get a little bit much forward with integrating additive manufacturing into the built environment. This is very much again what we're about to see. We have a first session that is dedicated to deep dive research, which will show you the very latest developments. We also have a session dedicated to computational design, which will demonstrate what's the point of additive manufacturing for the built environment, what can be crafted with it. And finally, Mission Meets Reality will introduce you to the latest integration in the industry of additive manufacturing. Before we start today, there's coffee over there. You're very welcome to help yourselves during the breaks. A very short also ask. You've been asked to register at the entrance on the list and to sign your name. It is crucial that you do it for us to keep getting the German research funding that we receive for the conference in support. Please remember to do it at some point. Philip, what am I forgetting in the practicalities?
I think we're covered with that. I think I'll take over from here. Before I start making a few announcements this morning, I want to thank Nadia this year in particular because she put together the program, communicated with all you speakers. She's really the head behind this year's symposium. So thanks a lot, Nadia. This is amazing. We're all happy to be here. And now, before we welcome our first session chair onto the stage, I want to just make a few announcements and show you a couple of things. We have an amazing series of books that accompanies this conference, our Beam booklets. They become thicker every year. They have all the essays of our speakers. We have an exhibition that I don't want you to miss out. It's in Hall 11.0. Booth F49, go check it out. Everything on that exhibition is in here as well. It's a super cool lookbook. If you collect the books over the years, they come in matching colors. It's an amazing feature. If you want to grab one, they're for sale for 10 euros out at the door. Highly recommend getting one of those. And then I want to show a book that we introduced last year at Beam. It's called print architecture. It's a book where we put together about 10 years of research in this field, from the very early, say, footsteps of additive manufacturing for construction to the large-scale prints that we're seeing today. By the time we published this book, we felt like it was outdated because the field is moving so quickly right now. But a great piece of, a collection of all the things that happen in this field. Amazing coffee table book. I have one at home, also for sale out there if you want to check it out. And then this was last year. This year, I want to introduce AM Perspectives to you, a new book series that we're launching. It's a pre-release because, as you can imagine, getting these things done in time is always a hassle. So the ebook is almost ready, but it's not printed. What is AM Perspective? AM Perspective started in Guimarães last year when we hosted a PhD workshop seminar with all our PhD students. We got together and talked all things additive manufacturing and automation in construction. This was our conference program. We invited a couple of speakers, international speakers, for input for our PhD students mainly. But we noticed the content that we presented, that we collected, is actually so significant that we asked this entire group to put together a book of essays on their work, on their current research. Then we went in Casoso in Italy, tried to sort through all the content and compiled all of this into a book that I want to introduce to you today at Beam today. It's called AM Perspectives. It's volume number 1. We're aiming at releasing this annually or biannually. It compiles content from different perspectives at additive manufacturing and automation and construction. We divided this into so-called realms. One of them is the fundamental realm. We have articles such as carbon-driven design of 3D concrete printed horizontal structures. As you can imagine, that's challenging. Just to flip through a couple of those pages gives you an illustration of what's going on here. It's a real cool way to stay on top, ahead of the topic. Just look at this. And it's going to be released very soon. Just wanted to set this up. All right. After these announcements, I want to welcome our first session chair to the stage. I will not introduce you because you have a 10-minute slot to introduce yourself. So I'll just hand over the microphone to you and kick off the program today with this officially. You're welcome to Beam 2023.
Okay, good morning everyone. It's my pleasure to kick off today's first session of Beam 2023. So I'm going to give a short introduction about additive manufacturing research. So generally, I'll just talk about a couple themes. We know that with additive manufacturing, we now have access to a wide variety of complex shapes. Indeed, there are a lot of examples out there that are using this functionality or this possibility to create strong and efficient structures using less material. And also, given today's climate, it's becoming more and more relevant to use bio-based materials and to use natural materials such as soil and earth in order to help mitigate the climate crisis. And increasingly, we're seeing more and more research that is controlling, adding advanced functions into materials, such as controlling its shape by arranging the materials at a mesoscale. So here, this is, yeah. So here you can see that the 4D printed parts are able to autonomously change shape on their own. So interestingly, I think we see a lot of this actually in nature. So you see a lot of examples of natural materials that have this differentiated structure. They're also based out of natural materials such as wood, other biopolymers, and they're able to autonomously change shape, react to the environment to perform a variety of very complex tasks, such as seed dispersal. And I'll just give a short introduction about my research. So I'm Tiffany Chang. I didn't say it earlier, but I'm a research associate at the Institute for Computational Design and Construction at University of Stuttgart. And so what we are mostly doing is trying to strive for this integrated material, structure, and function that we see in nature into our engineered systems. So what we do is we use bio-based materials, either we co-engineer them or use off-the-shelf materials. We arrange them in bio-inspired structures. The pine cone, as we saw earlier, is a very big inspiration that we often use, and we are mostly looking at programming a responsive function to allow these structures to autonomously react to changes in humidity. So, for example, closing when dry and opening when humid and wet. So we've investigated this theme at various scales. So we have done this a lot at the desktop hobbyist 3D printing scale. A lot of these functions that you see, this movement can only be achieved by these intricate structures, which we are able to create through an integrated combination of computational design and digital additive manufacturing. We also explored this at large scale, so on robotic additive manufacturing scale, so structures from 3 meters to 12 meters in length through our facilities, using the additively manufactured structures and patterns in order to create new functions such as controlled Gaussian curvatures, controlled curvature from double to negative to zero Gaussian curvature as well. And so now I'll give an example of how this can be applied to the built environment, to architecture. So this is a recent project that we did, which really shows this integration from materials to structure to function. So this is a project that is currently on the University of Freiburg campus. And what we did is we co-engineered our own materials. So here we are using cellulose, which is the material that we find in wood, but we mix it into a polymer so that we can actually 3D print with it. We also developed our own computational fabrication tools in order to develop a workflow so that we can apply this material with its unique properties to bio-inspired functional structures that we can control the bending curvature, the direction of bending, and the orientation of bending. And through this, we can create very fast reacting material systems. So here is a 4D printed aperture, which is actually very sensitive to humidity because of the cellulose content that we created. And as you can see here, it's even oscillating with the slight, I guess, the humidity in order to quite regulate the interior microclimate as well. And it's so fast that it can even catch up with these little fluctuations. So what do we do with this? We sought to then apply this to a building facade and use the cell shaping mechanism or the 4D printed mechanism to respond to the weather and to block the sun when it's very hot and dry, and during the winter when it's very very cold and humid to actually open and let in the free heating from the sun in order to create a comfortable space, a comfortable climate within the building. So this is just an example to show that because as buildings account for a very big chunk of the emissions, the global emissions, globally, it's of critical importance to reduce the energy we're using for heating and cooling in order to help mitigate the climate crisis. And so what I show here, and what you will also see in the following presentations, is how additive manufacturing can be used in the different areas of material, structure, and function in order to solve a lot of these pressing challenges that we're facing globally. So with that, I would like to welcome our first speaker. So Professor Dirk Lowe is a full professor at yes, okay, so welcome. Dirk is a full professor at the Department of Materials Engineering in TU Munich since 2023, October. Prior to that, he was also full professor at TU Braunschweig of the Institute of Building Materials, Concrete Construction, and Fire Safety. And he's an expert in colloidal interactions, rheology, processing and durability of concrete, as well as the technology of high-performance concrete and additive manufacturing. So today he's going to be speaking about additive manufacturing in construction and what are the challenges of going large scale.
So I was supervised to stay exactly here. So please apologize for that. You will not I see a lot of you, but most important is of course the topic and the topic of issues on the slides. So welcome, ladies and gentlemen. Thank you for the last introduction. My name is Dirk, and as you was told, I'm a professor for digital application technologies at the Technical University in Munich. And today I want to talk about additive manufacturing in construction and the challenge of large scale. The title of this presentation is exactly the title of our TRR 277, which is a G-funded collaborative research center. And saying that, it is, I'm here, or I'm presenting today on behalf of the board of the TRR. As here is the spokesperson, Katja Löffler, and of course I'm here to present on behalf of the researchers of the TRR 277, which you can see here from our last meeting in summer at TU Munich. So since I'm kind of the speaker today, I'd like to put the whole topic into maybe a more general view, and I want to start with this graph here, which shows the population development in the world. And when I was born, it was somewhere in the middle of the 1970s. There were about 4 million people on this earth. And some months ago, you probably news, we exceeded 8 million. So there's a steep increase in population on the world.
You have audio from this corner.
In 2091, experts estimate to have
You should mute the webcams.
10.4 billion people on this world. And this increase in population means that we have an increased need for construction. These people need housing, these people need infrastructure. In addition, we have an increase in prosperity in the developing countries and in China, and this again increases the demand of construction in the future. There's no doubt about that. On the other side, we know that we have a climate crisis, and to mitigate this crisis, we have to reduce emissions and resource consumption. And the great challenge for the construction industry in the next years or decades is to build more with less resources and less emissions. However, construction is not prepared for this challenge. As you can see here, since the 1970s of the last century, the productivity is almost constant. We have not developed in construction, we have the same productivity than in the 1970s. And on the other hand, with this technological, or with a stillstand in technological development, we are less attractive for young people. It's the second problem we have. Young people are not anymore keen to become a civil engineer, for instance. So if we have a look in other industries, we see there is huge progress in automation. But on the right side, in construction, we still have this huge amount of labor activities on the building side. And digitalization has not arrived the construction process far. Also, there were some progress in the planning phase. I think a lot of architects are here, but as we come to the building side, this break in the digital chain and the real construction process is not digital.
But is it working with the echo?
So the more you have a look on the right side, you see typical construction elements with concrete here, and these are often characterized by mass-intensive and resource-consuming geometries, and this means we have high CO2 emissions here. So the good news is, with additive manufacturing, promising construction technology is emerging right at the right time here. Then, because we believe that technology of additive manufacturing can help solving a lot of the problems I mentioned before. With additive manufacturing, for instance, you can significantly increase the automation in the construction industry. With additive manufacturing, you have no need for special tools if you want to produce different shapes or different forms. So we can produce shape and form optimized concrete elements, which results in a reduction of resources we need for these elements. And there's research where you can see that the reduction of masses in concrete construction, for instance, could be up to 50%. Well, and this is precisely where the Collaborative Research Center, TR277, steps into. The TR277 is, as I told, a research on additive manufacturing in construction, and we have been investigating the additive manufacturing technology since 2020. So we are now in our 4th year. And the mission statement of the first funding period of this research program was the challenge of large scale. Because what distinguishes additive manufacturing in construction from other additive manufacturing technologies in other industries is exactly the large scale. There are a lot of challenges which result from the large scale, and that's why we need special solutions for additive manufacturing in construction. Let me shortly introduce the TR a bit more in detail. The research is structured in 3 focus areas. You see here in the middle, the focus area R is materials and processes. Then we have focus area B, computational modeling and process control, and focus area C. You don't see my mouse, so maybe I should do this. It's a good one. And we have focus area C, which is design and construction. In focus area R, we fundamentally investigate the interaction between the processes and the material properties. And focus area B, we then systematically enhance this research by numerical modeling. And in addition, we have a focus on controlling of the processes and the path planning. And in focus area C, we finally investigate the interfaces between the AMC processes on the one hand side and the prior design and the following construction site organization.
In TRR, we intend to cover all additive manufacturing processes. As you can see here in the middle part, we have basically two main process technologies, the particle bed technologies and the deposition technologies. And we aim to cover all important materials for construction. So this means we are doing a lot of research on concrete. So this is the most used material in construction. Then we have research on earthen materials, of course steel and metal materials, fiber materials, and we have a project who's focusing on wood 3D printing. And let me show you some insights of our research. So here you can see some of the processes and the process material combination we do research on. This is the concrete printing process, shotcut 3D printing, and here you can see we think about how to integrate the reinforcement into these processes. Then we have concrete extrusion and clay extrusion processes. Mobile robotic is a big topic in our research. Then here you see particle bed technology, another interesting technology to produce really high resolution objects and objects with a high freedom of form. Another project is this selective cement activation, and we go even higher in scale, and we investigate the large particle printing. Then we dealing with new technologies like this injection 3D printing. We will see more here in this conference. And of course, earthen 3D printing, another important topic. Here you see automated ramming process. Wood printing. Here we developed a structured timber process by individual layer manufacturing. And of course, steel as the second most used material in construction. So here we are looking both on the deposition techniques. Here you can see a wire and arc additive manufacturing technology, and on the powder bed techniques, as example, here you see a part from laser powder bed fusion. So that was a short first impression of our research. I don't want to go into detail here, but you have in total 10 projects in focus area R, which covering these process material combinations. So shortly, we have A1 and A2, which are focusing on particle bed techniques with concrete. We have A3, which investigates a near nozzle mixing extrusion process. And we have this shotcut process we saw already in the video. Here we have a big focus on reinforcement integration. Then we have a separate project which is focusing specifically on how we could integrate reinforcement with fiber winding processes. Then, as I mentioned, the steel in A6 and A7, steel additive manufacturing, timber in A8, and then we have this new technology, injection 3D concrete printing, and the earth additive manufacturing. Well, you see there's a lot of material projects combination. Then we have this research in focus area B and C, and the big challenge in such a research center is how to combine all these projects and how to bring the researchers to collaborate interdisciplinary. And here we developed an idea that we put a demonstrator in the center of our research, and all projects of the TRR can contribute to this demonstrator. As I told you, these demonstrators are large scale, so we are aiming to produce real building elements in the one-to-one scale, and all the projects of the TRR have to bring the expertise into these large-scale demonstrators. And now I will show you 3 examples of these demonstrators. In total, we have 9 large-scale demonstrators. If you're interested, then I invite you to have a look on our homepage. They can find all 9 demonstrators, but today I did a selection of 3 demonstrators. And let me start with our particle bed technology. You see it here in A01. This is the technology, the selective cement activation. technology developed in the TRR, where you bring a binder and aggregate in a particle bed. It's a dry particle packing, and then you activate by applying water on the distinct areas to harden the material. And this technology is characterized usually by really small building chambers, so it's not even close to construction scale. What we did is to increase this to the large scale, and fortunately here we have two industrial partners who built a large scale printer, and another partner who used this printer to build together with us this real scale element. And as an example, there was a design from the architectural department. We used this facade element, which you can see here. It's inspired by the architect Marcel Breuer, and you will see it later. It's a round-shaped building, and the function, or one of the functions of the element, is to have a natural shading depending on the location in the building. So each facade element has another geometry, and that's perfectly for additive manufacturing, because you can be really optimized in relation to the position of the facade element. Then we have further functions here. You see a microstructure on the surface, which is kind of micro shading, which helps to reduce the temperature on the building element. Then we have parts here in the middle of the element for thermal insulation, and at the back of the element we have the structural part of this facade element. And let me show you these videos that you become some impressions of the production process. This is the final element after production. So it's about 2.80 meters, I think, or even higher. Here you see the design is the building. These are the facade elements, and we picked one of the facade elements to produce it with selective cement activation technology. Here you can see the different functional areas. You have this structure, then you have this thermal area in the middle, and you have the structural function and the back of the element. Okay. Of course, we did some research on the material. I will not go into detail into that. It's more about the production of the big element here, and here you see the 3D model, which are then got into a large scale particle bed printer. It's 4 meters by 2 meters by 1 meter, so it's really able to produce this element in one part. And yeah, to increase the structural or the load bearing capacity, we combined this printing process with mixed concrete. So we use part of the element as formwork to integrate the reinforcement in this case, and to increase the structural load bearing behavior. So this is the part in the back, or the inner part of the element. You can see the great advantage of these particle bed technologies is that you can really have high resolution surfaces, and you are really free in printing forms like hollow structures. Then we filled this structure with insulation material, and this is the final element. Okay. The second example is still in this lower area. It's printing with concrete, and we showed what we can do with the shotcrete 3D printing process here in A04. And therefore, again, at the beginning there was a design process. It was this building here, you can see in the upper left, and we took out some special part of this facade again, and you see here this column and this wall element covered with a ceiling element. And on the right side you see the process. It was printed in the digital building fabrication laboratory, again in a 1-to-1 scale. And again, you can have a look into the process with a video. So this demonstrator is called Shelltonics. And of course, we printed with integrated reinforcement here, because if we are talking about concrete 3D printing, then we always have to think about how to integrate the reinforcement, and we added a second layer, a vertical layer, to smoothen the surfaces. As in conventional technology, it starts with producing the concrete, of course, and then the 3D printing processes start. So the column and the wall element was produced at the same time. And here you can see how we integrated the horizontal reinforcement. Was done by hand here, but you can also imagine to have it with the pick and place process by the roboter. And the vertical integration was done fully automated with this short rebar insertion technique. Here you have some impressions of the surface smoothening process. And at the end, the second layer or the cover layer is applied on the surfaces, and you can create a quite nice concrete surface. The second reinforcement process we used here was this fiber binding process. You can see here, so it's fiber wounded around the column and then covered with the cover layer to get the bond between the reinforcement and the concrete element. And this is the final product. So we ran out of time, so the ceiling was not ready at the time. We had to show this demonstrator, but we will produce in the next funding phase. Okay, the last process I will show you, this is a quite interesting process, and you can see, oh, by the way, this project A01, the facade element, the Breuer facade, will be presented later today, and also the project which I show you now, the injection 3D printing process, there will be a specific presentation here in this symposium later. So the injection 3D concrete printing process is a quite novel process. It's a process we developed at TU Braunschweig, and the idea here is that we inject material into a carrier fluid, and this carrier fluid is somehow holding the injected material into position. So the material is not sinking down or swimming up to the surface, it's really hovering at exactly the position where we printed it. And the big advantage of this technology is that you can get rid of the layered structure of 3D printed elements, because you now can really print freely into the space wherever you want. So if we are honest, then the other techniques are more 2.5 3D printing, and here we have real 3D printing because we are going into space. And what you can produce with that technique is, for instance, these elements is really filigree elements, as you can see at this bridge example. And again, we will have some questions here in the video. So this is the design. The basement was produced by particle bed printing, and the bridge structure in the middle by this injection 3D concrete printing. Here you can see the path planning of the bridge elements. These bridge elements were segmented and produced in smaller parts. And here you can see the printing, the principle of the printing process in a gel, that you can see the concrete. But of course, the gel is too expensive, so we developed a suspension made of limestone where we print in, which has the same properties, the same rheological properties than the gel, and we print into this muddy container here, the bridge structure. At the end, you have to remove the limestone suspension. It's not reacting in any way, so you can use it again for the next production process. It's only stone powder and water. Then you have to clean the object. Then we 3D scanned the bridge elements to 3D print again some connection elements between these segmented bridge elements, and then we assembled the bridge in a collaborative effort. So we needed a lot of researchers from the TR to bring it in form, and this is the final product. Okay, these were 3 impressions from our research. If you have further questions, please ask me now or in the coffee break. And last but not least, I want to use this opportunity to make you aware of a nice conference next year in Munich. So it's a digital concrete conference from the 4th to 6th September. And I all invite you to send abstracts. So the abstract submission deadline is soon, 22nd of November. But if you're a bit late, please write me an email. I'm sure we can manage to include it in the conference. So I hope I will all see you there next summer in Munich. Thank you very much.
Hello. Okay. Thanks so much, Dirk, for your great presentation. You presented a lot of very interesting topics and projects. Are there any questions from the audience? It's a great chance to ask in person. If not, I will start with just a question about, okay, you've presented how you've tackled some of the challenges through the TRR, and what do you think are the next challenges?
Of course, we are applying for a second funding period, and we choose a new motto for the second funding period, and it was the chance of a great impact. So what we mean with that is the impact on construction industry to really transform construction, and of course the chance on the ecological side to really reduce the environmental impact. So first, of course, by form optimization. I showed you this in this presentation, but a big topic in the second funding period is how to reduce the carbon footprint of each of the material we use for 3D printing. And here we are planning for going into the direction of net zero. And yeah, look how far we will come in the next 4 years.
Thanks. One question here.
The question about the material you use, so is it self-designed material, or do you work together with industry, and how do you keep the quality of the material at a certain level in these experiments and prototypes?
We use both. Of course, we have fundamental research. That's why we really have a deep look into the material. I didn't present anything about that topic, but we really go to the nano scale to improve the material. But especially or in particular for the architectural context, we use industrial material because printing this large element, you need a lot of material and you cannot produce it at the university. So we have industrial partner for that, and we have material research for specific questions. Yeah, and quality control is a big topic. And here we are trying to go the way that we look or do research how we automatically control the quality by having inline quality control in the printing process. That's the vision we have, and we're working hard on it.
Okay, thanks. Thank you so much, Dirk. I think we have to actually move on to the next speaker. I'm sorry, but yeah, you should ask after in the breaks. I'm happy to introduce our next speaker, who is Andreas Trümer. Can we switch the presentations? He's an associate professor at the TU Graz at the Institute for Structural Design since 2015. He's also head of the Roboter Design Labor, the robot design laboratory, and heading that since 2010 with a lab with capabilities in 3D concrete printing, grinding and milling, but also robotic welding.
And he's also had other appointments, such as a research fellow at the Harvard University Graduate School of Design in Cambridge, USA. And he's going to be speaking about lightweight reinforced concrete slabs with integrated 3D printed formwork. So with that, I will hand over the stage to Andreas.
Okay, good morning, everybody. Good morning, everybody. Thank you for the nice introduction and the invitation to be here today and to share some of our results from a research project or a research period of, I think, about approximately 6 years. And yes, today it's an honor for me to represent the Institute, and the research group is working on that. And yes, it's a funded project, it's a national funded project. In Austria it is FFG, and we work close together in this project with industry partners. Yes, and it's super nice that Georg is accompanying me today. So if there are questions that go deep into the topic, then we are together here to answer your questions. Yes, for today, I would like to present we try to give or to name it the Grazer Stahlbeton-Leichtbauweise, or lightweight reinforced concrete slabs. And it's the story about a dissemination process from research to clients and industry partners, and how we can work together to bring these ideas that we deal with, all of us, that we try to contribute with digital fabrication, additive manufacturing, structural design, and architectural design to improve or to change our construction thinking in the next years. From the additive manufacturing side, so we started in 2017, and we came up with our own material mixture. We built our own printing nozzle for this extrusion process. Then we changed and did some tests with concrete and cement-based foam. And in the end, we ended up with this inside prefabrication of slender prefabricated elements that we use as a kind of lost formwork. And this was the challenging question about material and process. And the other hand is how we can contribute to the question of this enormous amount of material that we use in our everyday construction sites and the infrastructure building that we need. And we know this is everyday life. So thousands of square meters, approximately 5 million square meters every year in Austria of concrete slabs that comes up new. And we also knew from our last speaker that there is not the amazing change of technology over the last 50 years. So we do it quick, fast, safe, but it's material consuming. And when we have a look into material and the material use for residentials and office buildings all over the world, it's significant that in Europe we use an enormous amount of concrete, but all over the world for office building we do the same. So it's a global question, but we can contribute as a local group of designers and local material distributors and construction industry. And this was our first guess or hypothesis that we would like to change plates and slabs for floors, reducing and take out material up to 40% with the method of this ribbed Kassettendecken, and it was the idea that we can keep the height and that we keep the performance and that we can take out just the material. As a first guess, it was reduce the self-weight by 40% and keep the performance as it is, taking the same height. As a first result of our research project, a 3-year lasting one, we came up with this prototype and this demonstrator, and we looked back and took the design of Piero Gineri, so it's well known, and cut it out, this piece of element, optimized this rib slab with the goal that we do a bigger prototype that we can test in our lab. We produced all these elements in our Roboter Design Labor. And prefabricated this testing piece together with our partners from industry. Did the reinforcement work, and here you can see that there is some effort in this reinforcing of the ribs, and then we put in normal concrete to get the strength. And as a result, we could demonstrate that we reduce an amount of concrete. This is the white block. We have the same amount of steel reinforcement, and there is an additional amount of CO2 equivalent brought into the construction by this printed concrete. So we should never forget that this is high quality concrete, high strength concrete, and it's approximately the double of amount of cement in this mixture. And outgoing from this demonstrator, we got the opportunity for a first design proposal for an artist, Hans Kupelwieser, and an atelier in this castle in Upper Austria. And again, we did this design part for a 10 by 10 meter atelier room, 100 square meter, and it was, together with the artist, a process of finding a ribbed design and solution, and we came up with this proposal here. We did all the structural calculation and optimization process, and in the end we did all the print path generation and the production in-house. And you see the quality of the printing material, the quality of the surface is changed. So it's our partner from industry is Baumit. So this material industry, the bigger one in Austria, and their department for 3D printing is working with us close together and do a lot of funding for all this work here. And all these elements in the end find their place at the scaffolding, and we had a lot of effort in reinforcing all the ribs. It was some nice struggle to be there for 2 weeks at the construction site, and in the coffee break you can ask Georg about some stories about working in this wonderful site there. But in the end, we came up with this Rohbau view shortly after the scaffolding was removed, and now it's a place for art and art pieces, and we are yes, we are happy that we could contribute in this project. But as a result, concerning sustainability, you can see here that we again removed some concrete material compared to a flat plate and slab, that we could reduce the amount of reinforcement, and there is another, again, some more CO2 equivalents coming out of this printing material. And we see here that working together with the client, the engineers, research and the industry brings things together, and we got a lot of information, a lot of questions out of this project again. And some of you know this project again with a client that is working together with Permit. So it's a smaller construction company in Bavaria. They own their own printing facility, and we come together to, yes, to contribute to lightweight structures and think about and had a discussion about how we can bring that into the construction site there. And it's a roof over a garage, and it was the question how we can take out material to make it to a lightweight concrete solution. Here you can see Theo Graz contributed. It was Engelsmann Peters' office, Baumit GmbH, eigener Bauunternehmer, so he was the man. He did it in the end, and Merker Transportbeton. And all together worked hard to bring that to real. And our part was the design again. And here you can see that it's a single-span cantilevering structure, and we came up with this kind of a canoe-shaped design. And we did all the pre-tests for printing strategies, but in the end, the construction company did all the printing. So it was the transfer from research to industry or to the construction company. And they had the facility quite close to the construction site. Again, it was the assembly process that in this case it was pretty simple to do that, and the reinforcement and additional concrete work that has to be done. And again, we did some calculation about the resource efficiency and the CO2 equivalents, and you can see here that we came closer to a goal that we can reduce CO2 equivalents by a rate of 40%. And why is this possible? So we reduced the amount of concrete. We used different concrete, so it's binder reduced, cement reduced concrete as the poured in concrete. Again, you see in magenta the amount of CO2 equivalents coming out of the printing material. We took out the inclination insulation part, and we reduced in a bigger amount the reinforcement that is needed for this roof construction. Yes, and we are proud and happy that today we can go for Düsseldorf to gain the German Architecture Concrete Award for this project today. And that means that concrete printing and additive manufacturing bringing into construction will be honored in Germany, and that makes us happy to be there with all the team that was responsible for this project. And it was possible in this constellation to do another building. It's Verit Werkhof in Vorarlberg, Austria, Bludenz. So it's approximately 800 square meter, and it was a similar constellation. So there was the architectural office Atelier Ender, it was GBT, Ziviltechniker engineers. So the planning team was existing, the design was done, and the Tomaselli Gabriel Bau construction company owns the concrete 3D printing company, these two together with the material provider Baumit. Asked Institut für Tragwerksentwurf for contribution to make this roof lighter as a lightweight structure, and we could step in and give some support to change the construction for this ripped solution, and we came up with this around 800 elements that are printed and placed for this approximately 700 square meter roof. And all the elements are different and find their place. And you see all the reinforcement work that is now better and better and more efficient. And we are happy to show you the result for this integration of 3D printed hybrid structures that are lightweight and can contribute to the questions of sustainability as well as additive manufacturing. And again, we did this post-calculation for the CO2 savage, and you see it is a span of 40 meters, as higher the span, as more efficiency we can gain. You see this white column is the reduction of the amount of concrete that is poured in. The blue one is the reinforcement that could be reduced. The magenta one is the additional CO2 equivalent coming out of this printed material. And so it was not possible to use binder reduced concrete for the additional poured in concrete. But if it would be, if we could manage that, it would be possible to reduce the amount of CO2 equivalents by around approximately 40%. All these four projects together summed up around 60 tons of CO2 equivalent, and take them out of these concrete slabs. And all these four projects asked a lot of research questions that came back into our research projects. It was about a lot of printing tests and printing strategies, how we can manage in a safe way these lost formwork pieces. Here are some of the tests for the Nördlingen project. It was the big opportunity of testing one-to-one scale about the mechanical properties. This was from the first Quebo project. And we worked close together with the Department of Civil Engineering and their testing facilities. And the same was done for the Nördlingen project, that we could cut out one piece, produce it in the place, bring it to our testing facility in Graz, and do this one-to-one scale test. But it was not only about the question of strength, it was about fire resistance. So we did a first one-to-one scale test of 1 square meter that gave first answers about the bond between the printed concrete and the poured-in concrete. And you can see here the results. That is a perfect bond, and the fire resistance of this printed concrete is super high. And of course, we did tests about the bonding between the two materials. With these small scale tests. And additionally, we did Carbonatisierungstests for printed concrete together with this poured-in concrete to get first information about these properties. Concerning the fire resistance, it was possible in this project, in this research project, to do bigger one-to-one scale tests of one of these slabs. So we produced it, and it is loaded and under fire for more than 120 minutes, and it's full resistance for all the needs for fire resistance. It is REE 120, and that opens the field that we can use this kind of slabs for residential and office slabs as well. And so I cannot show it now, but so we do similar tests for acoustics, that we get the answer what is the best way of floor design for this kind of slabs. Yes, coming to an end, we do that in a bigger group that I can represent today. On the left side is the printing group. It changes all the time, but it's a small group of architects, civil engineers, material scientists, and industry together that work on these questions. On the right side, we founded a research center for sustainable construction at the TU Graz that helps us a lot to answer the question about sustainability in construction. And it was one goal not to design research pavilions in this project, but finally we did it. And I can show you first pictures and first 2 slides of a research pavilion about 10 by 10 meters, again 100 square meter, in the place of Baumit industry in Niederösterreich, close to Vienna. And it was the opportunity to use this idea of lost formwork for walls and slender columns again. So we know a lot about these grids for the slabs, and now we have to do first steps into other kind of structural elements. Yes, thank you for listening. If there are any questions right now, feel free to ask, but we can do it during the coffee break as well.
Thank you so much for this really nice presentation. We have one question.
Thank you very much for this wonderful presentation. I have one question about the printed concrete of the mold. Is it considered as load bearing in the structure, or at least considered as concrete cover for a reinforcement?
It is considered as the concrete cover, but it's not load bearing.
And
So
do you any plans to change this, to any ideas to bring it into the structure as a load-bearing material?
Our test showed that the cracks in the concrete, in the load-bearing concrete or in the poured-in concrete, and of course in the printed concrete are the same. That would mean that they work together. But right now we cannot use the higher performance of the printing concrete in these load-bearing questions.
And a second one, do you have to secure the printed molds in the concrete, or is it just hold by friction between the two concretes?
During the construction phase, or?
No, in the service phase. Is there not the danger that they are falling off, the mold elements?
No. So all our tests showed us that they are not falling off after 120 minutes of 1000 degree centigrade firing. So there was some elements that fall down, but it was no collapse. And I think the bond is, so we tested the bond, and the bonding between these two concrete hybrids is perfectly.
Nice. Thank you.
Hi, thanks for the presentation. I think you bring up a very nice point that you said that we wanted to test our ideas on actual building projects, and that of course brings building regulations into the conversation. So it's really nice that you show all the custom tests that you've been doing, structure and fire and so on. But I'm wondering, like, from a larger perspective, do you think there is any way to not have to do a custom test every time anyone needs to 3D print anything in a building? And what's the way that these would be integrated within the regulations of the building code in a more general way, the same way that we see standard elements having not to be burnt every time you need to use them in a building?
That's a super important question. I think all of us are suffering a little bit that there is no regulation, no standards. We are now discussing about. So what is a good one printed element? So think about, I mean, there are around 900 elements coming to the construction site. So all of them should be safe, and it should be clear that they are the good ones and not the bad ones. And so when we would like to open the field for architects and engineers in these design stages, we have to do a lot that we get control about the material and the process, and in the end the engineering for that. And we work on some standardization that we know more about the material. And I think all of you know that when you do mechanical testing on small pieces, that is depending on the size of the element, and there is no common agreement about what is the good test for especially additive manufactured elements. And there is, I think, for the next year a lot to do, that we bring it in this world and it is not separated from them, that we have always to test things. One way or one strategy is do a combination of well-known reinforced concrete work and 3D printed elements, because we sleep very well with this kind of construction, because it's completely in all our standards and all in our regulations. And it's just a question if there is some printed elements, can they fall down or not, or do we change any properties concerning building physics, when we came up with this old idea of ripped slabs that we built in the 60s and in the 50s, or in the 1920s, these super early concrete slabs. We found one in Vienna, and we did this calculation for the CO2 equivalent, and they are much better than that what we can do now. And we have a lot of trouble, some of you know, that we can recalculate this early concrete work, but it works for around 100 years. So we are in discussion, is there some failure in our thinking about design or what? And we have to do this discussion for the next years.
Thank you so much, Andreas. We'll have to move on to our next speaker. her. It's my pleasure to introduce Inka Fani, who's a junior professor at the Institute for Civil Engineering at TU Berlin. Since 2023, February, she's been heading the Department of Robotic Manufacturing of the Built Environment. And she also had completed her doctoral studies at the TU Braunschweig. Prior to that, she studied in the Université de Bretagne in France, Chalmers University in Sweden, and University of Rhode Island in the USA. She'll be presenting on injection 3D concrete printing, and I pass on the stage to you.
Okay. Thank you, Tiffany. I would like to welcome you also from my side, also on behalf of my co-authors from TU Braunschweig and TU Munich. And I would like to introduce today a little bit more in detail the injection 3D concrete printing technique, with which you actually have the possibility to explore also new potentials in concrete 3D printing. And before starting directly with the deep dive into the injection 3D concrete printing technique, I would like to mention a little bit how you can explore the new potentials. So conventional 3D concrete printing, as you currently know it, there you subdivide between 3 topics, which are basically extrusion, material jetting, and selective binding. You already heard about the techniques earlier in the first presentation by Dirk Lucke. So in extrusion, we mix our material, we deliver it to a nozzle, and then we apply strands and stack them upon each other. In material jetting, as for example with the shotcrete 3D printing technique, which is shown here in the middle picture, you basically follow the same route with the difference that you add pressurized air, for example, in the nozzle. But here you still add the material layer by layer. And then, of course, you have selective binding. But before, I would like to give you a short overview about the kind of limitations that we are facing in extrusion and material jetting. So we are stacking layers upon each other, mostly in the vertical direction, only to a limited extent, also incorporating overhangs. So we are a bit limited due to the material properties, what is regarding the geometric freedom, because there might be a risk that you have a collapse. This is actually not exactly the case for selective binding, where you apply a layer of unbound particle bed and then you locally activate it by incorporating, activating fluid, which is then in the end building up the structure in a vertical way. So to show a little close up here, you already see what I'm talking about. So you mainly are talking about horizontal layers, and this is something which is somehow limiting the freedom of form in I call it conventional concrete 3D printing. And there's the possibility of overcome this limitation by the injection 3D concrete printing technique, which I would like to introduce here with a short video from TU Braunschweig and TU Munich. So this is actually gives the possibility to also print directly in 3 dimensions. So you have the possibility to spatial 3D print without any geometrical restrictions due to the vertical stacking of layers. So this is something that you've already seen in the first presentation today. But I would like to give you an overview about the basic principle of injection 3D concrete printing. So very first, I would like to show you the potential process. So you usually mix your material, I call it now material A. You mix it, you pump it through a hose to a nozzle, and then you deposit it in a vessel where a material B is placed. And in this case, the requirement is material B supports the injected material A. And now I'm very cryptically talking about material A and B, and you may wonder, what are these materials? Or I would like to open up the questions, what can these material be? And then we come up with this matrix. So we have a material which is supposed to be injected, and we have a material which is called the carrier liquid. And then you can have either a hardening material, concrete, or you have a non-hardening material, which I now call non-hardening suspension. And this can be basically every material which in the end exhibits a yield stress. There has been already some research about it, and the Glocke showed already earlier and mentioned that this may be ultrasound gel, which is nice because you can look through it, and for the video which I just showed earlier, it's also nice to see directly the structure that you printed. But of course, there it can be also more sustainable materials like limestone powder suspension. You can use additives and many more things in order to also in the end consider a potential reuse of the suspension. So as you see this matrix, there are in total 3 feasible subcategories of injection 3D concrete printing, which are relevant for construction. Namely, concrete and concrete, suspension and concrete, and concrete and suspension. And as I'm aware that there are a lot of architects here in the room, I would like to start first with some applications of the injection 3D concrete printing technique, therefore I would like to start with the suspension in concrete, where you can see basically the technique where you fill your concrete in a vessel and then inject the non-hardening suspension into the vessel at specific locations. And after hardening of the concrete, the non-hardening suspension can be removed, leaving cavities or channels behind. And this can be used, for example, to grade concrete components by differentiating its density at specific locations. And in a small-scale experiment that is shown here, and their ultrasound gel or ultrasound mortar was actually injected in the formwork. In all cases, the displacement suspension had a specific volume, and this point pattern was followed, and in the end, the volume of the holes that were created were changed by also the variation of the extrusion time. So in this case, the printing was realized by printing also the holes from bottom to top. So I already mentioned that it's conceptually possible to grade material properties. This can be conceptually thought in this demonstrator as it was used for facade greening, and it's interesting if you are looking forward for spatial integrity while saving materials. And of course, you can consider additional function integration. The second subcategory I would like to introduce here is the concrete and concrete technique. And as mentioned earlier, you inject one concrete with specific properties into another concrete with different properties, actually. And the material properties may mainly differ according to the functional needs in order to locally, for example, strengthen the structure. So here is the only technique which is relevant and where you have a permanent mechanical bonding between the two materials A and B. And there's one beam in, let's say, a small scale, which has been already produced with this technique. And you can see that with one continuous path, you are able to combine two different materials. And this may be, for example, possible in order to combine, for example, an ultra-high performance concrete with a very ecological friendly concrete. This process took less than 1 minute to print it into the inner structure. So it is a fast process. But of course, this is also now on a small scale. In the future, we also would like to focus, of course, on larger scale. And if we are talking about larger scale, we have to also keep in mind what our material is doing over this time. And we are well aware that concrete is building up yield stress over time. And if we are looking forward to also produce larger structures, then we have to realize that the boundary conditions for our print are continuously changing. So we have an increasing force acting on the nozzle, and this way we may have to face potential displacement of the robot nozzle. It may be also more difficult to inject our material, and potentially we have issues to connect the strands of the injected material together. And as for all challenges, there are of course solutions that need to be investigated further, and there are already some on the way, and some of these ideas incorporate the concept of incorporating more than one robot, because you significantly can increase the print time, just as you can see here conceptually, that are more than one robot working on the same component in order to increase the printing speed. And the last technique, subcategory of injection 3D concrete printing, is the concrete in suspension technique, which was already introduced earlier today. So in the third category, it's the possibility to inject a hardening material into a non-hardening concrete, into a non-hardening suspension. And the main advantage here is that we are able to produce filigree structures. One of the first objects that have been produced here, in this case at TU Braunschweig, was this polyhedral structure, which is obviously very, very lightweight, but first large-scale applications have been already introduced. For example, by the company Soliquid, a startup from France, who produced this artificial reef called bathy reef with an industrial robot. And this bathy reef is supposed to increase the biodiversity in the sea. In this case, this example was installed south of Toulon in a depth of roughly 2.5 kilometers. So this structure is already at a large scale. Just to give you a rough number, I think there are 15 modules consisting of 30 to 100 kilograms of concrete. This structure is bio-inspired, but not mechanically optimized. In terms of mechanical optimization, there are also possibilities to investigate this further. And there is some research by Inan Xiao and his co-workers where he explored further potential by aligning the spatial stress trajectories aligning it with the print path. And here, in this case, a coffee table was produced, which by finding the design applying a method called vector-based 3D graphic statics. And 3D graphic statics is a design and analysis method for trusses under static equilibrium, and it provides visual information directly between the relationship between form and force. And with this method, it was possible to design a compression-only structure, in this case, this coffee table, which was produced in 3 elements, which were in the end, after fabrication, assembled. And with this, it seems like it is easy to master this process. But of course, this is actually not the case. So I would like to also give a short insight into learning from failures, or what you can also call material and process requirements for a successful print. And if you are into 3D printing, you most probably have also experienced the one or the other failure. And if you look in literature, then you see often some work which is already describing the failures. So for extrusion, for example, this can be these uncontinuous strands, which is occurring if you're, for example, going too fast with the nozzle, and then you have a local tearing. Or it can be because you're going too slow with the nozzle, and then you have this kind of buckling behavior or over-extrusion. So the case, this is actually exactly the same case for injection 3D concrete printing. If you have in mind that you want to print a strand which is locally stable in the carrier liquid, and it has exactly the designated shape, then you can kind of depict this kind of setup. And then you have two possibilities. You go too fast or you go too slow if you're not meeting the optimal extrusion velocity. And then you have exactly the same failure. You have either a discontinuous strand, an undersized strand if you're too fast, or too slow, oversized strand, and undulating strands. And this is a failure which is exactly the same as for the extrusion, which is already well known. But additionally, there's another failure mechanism which is specific for injection 3D concrete printing, and this is that you're kind of having insufficient positional stability. And then your strand is, for example, sinking to the bottom, and that's, of course, something that we are not interested in. So therefore, it is needed to also, of course, master the material properties. And just to give a very, very brief overview here, it is important to master the densities of the two materials, carrier liquid and the injected material. It's relevant how you have, what kind of a diameter you print, and of course the yield stress of the carrier liquid if of importance. And in the end, you have kind of a failure criterion, and if you're above the red line, then you can produce a stable print. If you're below, you're most likely unstable. Sounds like it is all solved, but this is, of course, also not the case at this point in time. So you have to think about what's happening directly after injection of the injected material, but it may occur that the carrier liquid may also change over time. And just to give you an example here, if you're, for example, considering limestone powder suspension, then you will experience, if you're not controlling it in the right way, significant sedimentation of the carrier liquid, meaning that you're locally changing the properties of your carrier liquid. And locally changing the material properties means that you potentially will experience a failure of the print at a later point in time. So it's important to also check how to master the material properties for a longer period of time. So this is what I would like to give you as an introduction into this combination between material and process. And I would like to actually conclude with a video from a successful print where we were involved into the production of this large-scale demonstrator, which is currently, this technique is under display also at the Biennale in Venice, this year, which is until this month. So here, it was the idea to produce also a large-scale element. It's in total a bridge, the first overall and large-scale structure, which has a length of 4.2 meters. Dirk Loco already showed some pictures earlier today. And with this, you can see that you, of course, can apply the vector-based 3D graphic statics, which has been here conducted by TU Munich. And then in the end, there were 5 modules printed. And here you see that in smaller vessels, it was possible to produce single components. And in the end, here it was not this ultrasound gel was used for the fabrication process, but it was limestone powder suspension which was, for at least the duration of the print, stable. And of course, after the fabrication, you have to deal with digging out the single components. You can lift these components out of the material carefully and then clean it. And as here are different modules which were combined, we also scanned the structure, produced single joints in order to, in the end, put the modules together, which was actually not done by robots, but still, this is manual fabrication. And in the end, you can see here the first above ground construction component, which is produced at all. And with that, I would like to also conclude my talk, and I would like to thank you for your attention. And if you have further questions, I'm here to answer them now or later. Thank you.
Thank you. I think that was really fascinating how you showed that really by mastering the process and the material, what we can enable with the structural design. Are there any questions from the audience? One right here.
Hi, thank you very much for the presentation. I have a question concerning the suspension in concrete method. It really struck my attention. How exact is the execution compared to the prior design? Because I imagine it to be not random, but you cannot really see what's happening inside. So how well is it, or how usable could it be for static application, or is it rather sculptural because it's not as reliable to, you know?
Yeah, I know what you mean. So at this stage of development, there have been only a very, very few experiments exploring this subcategory. So at this point in time, I would mention that it's not very exact. But if you really understand what are the forces which are acting, how to control the material properties, then you will be for sure able to exactly control where the material is placed and to create also components which are exactly as designed. So, but this, to be mentioning, this is just a few first experiments that were already conducted.
Thank you.
Any other questions from the audience? Okay, one more here.
Thanks, Inka. Super interesting. I really enjoyed the presentation. I was wondering, with regards to this last project that you were showing, what do you foresee are the next steps that you'll be taking in the research in order to, in some way, ensure replicability or scalability?
That's an easy answer. Reinforcement integration. Because currently, so if you design it perfectly and you print it perfectly and you definitely have a compression-only structure, that's easy, you can only work with concrete. But as soon as bending comes into play, you have issues of breakage of the objects, so therefore reinforcement becomes mandatory. That's the biggest challenge, but there are of course further, but to keep it simple, that's the next step.
Any other questions?
Very interesting lecture. I have a curiosity. Did you make some tests on the concrete strut, like compression or bending, just to evaluate their capacity?
No, at this point in time, we of course do know the material properties itself of the printed object, but we haven't done material load tests yet. That's of course something that will be
envisaged in the future, but yeah. So it's a rather new technique which will be developed further now. And then this will be one of the, of course, of the open questions which need to be answered.
We have time for one more question, so...
Thanks for the presentation. It was super interesting to see the trick. So, can you give us an idea of the scale boundaries? So, what do you think would be the biggest concrete element that you can extrude under these conditions? Or do you have a wish of a structured element in the end?
So, I think it depends basically on the technical possibilities that you do have. If you have large enough robots, then you can of course, or if you have a large reach, then you can you basically need to fill your vessel. I could also picture that you use, for example, the concrete technique on construction site. So just have your formwork there, and then there's a mobile robot printing into the formwork where you want to strengthen your structure. So I think we are not basically that limited. I think we are really facing large scale, especially with the possibility of mobile robots. We have a lot of chances to explore this even further.
Thank you so much, Nika, for the wonderful presentation. So now it's my pleasure to introduce Dinora Schulte, who is a adjunct associate professor at the Universidad La Salle, and she's also co-founder and principal of Manufactura, which is a multidisciplinary studio that specializes in the relationship between digital and analog manufacturing based on tradition. She recently graduated with a postgraduate master's degree from the ETH Zurich and has worked with renowned architecture firms such as MAD Architects in Beijing and Rothkind Arquitectos in Mexico and Ensemble Studio in Madrid.
There you go.
Perfect. So then, Dinora, I hand over the stage to you.
We have to.
Yeah, sorry about that.
Yeah, we have to switch the screen.
I'm a little bit like that.
Yeah, a moment. We'll open it with the.
Ready? Hi, my name is Dinora Martinez Schulte. I am a co-founder of Manufactura and also I'm professor in Universidad Iberoamericana, Ciudad de Mexico, and Universidad La Salle in Mexico City also. Today, I'm going to present my lecture, Building with Awareness. What's the fusion between tradition and innovation, and why we are working in terms of digital fabrication in Mexico. So I study in architecture in Universidad Iberoamericana, and also after this, I study a master in digital fabrication in ETH Zurich. And in the master, I have a lot of opportunities to work with different material, like plastic, local material, recycled material, textiles, etc. So I'm going to talk about a little bit of how the materials works and what's the impact of each material, and then how we are applying this in Mexico. So first of all, we work with PLA, with this, the 3D printing with PLA, this exercise called eggshell. For example, one of the best things in plastic, plastic dries really fast, and then you can get a really good precision. You can get also play with the shapes, with the, all the measurements, and then also we use the plastic as a formwork to cast concrete. So also in 2019, I worked with recycled plastic from the oceans in the robotic atelier by the Norman Foster Foundation. And in this case, we built like facade elements, and also these elements was directly worked for thermal insulation. And in this case, like the plastic, the recycled plastic also, it was very useful for this kind of assemble of disassemble in different directions that you can see in the pictures. And for example, as Norman Foster said, in terms of sustainability, it's not only the sustainability is about the material. It's also like to fabricate objects that it can be easily disassembled and assembled and transported to situ. And then in the MIS, we also do the digital bamboo pavilion, and then we work with 3D printing with PTG and fabrics. In this case, this pavilion was made by different systems like bamboo, the joints, and the textiles. And I was in the textiles team, and for example, we did a very big research about what's the kind of fabrics we can work with to 3D print. And at the end, we select like nylon polyester that also we play with the 3D printing levels of the plastic in the textile. For example, we play, when we have structural stresses, we have more levels of printing, and then we have like less levels of printing when we just want to do aesthetic effect. So in the joints, I was not in this team, of course, but it's also part of the project, and in this case, we also fabricate a very easily system that you can assemble and disassemble these bamboo structures, and then we built this pavilion in less than 3 days. This pavilion also, you can see what's the benefits of using digital fabrication and also like computer design together, and how we can create this kind of aesthetics, this kind of patterns. And this pavilion was exhibited in the Museum of Zurich of Architecture, and here you can see all the system working together. So the main goal of this pavilion is just to see what is the real structural performance and also design performance of a really natural material as a bamboo structure. And then we also work with concrete in this exercise called concrete calligraphy. In this case, we did a lot of facades, for architectural buildings. And in this case, concrete is totally different than plastic. Concrete is a liquid material, and then you can also have a non-stop printing. So what you have to do is just to design one single line of the pattern, and also you can have to use less than 2 intersections. So in concrete, what we did, we designed this kind of pattern that they joined in the joints, and then this is the final design. At the end, we select just one of these elements to 3D print one-on-one, and this is the result. Then we also started to connect these facade elements, not just in the interior and the exterior, to create a microclimate in the building system. Then, earth. Well, in this case, we did the second pavilion in the MIS called rapid clay formations. In this case, we use the machine as the constructor. We use also the precision and the labor force of the robot to connect and knit these air bullets. And also one student also fabricated the tool, and it was also using by pressure. At the beginning, this pavilion was planned to be in Brazil, but this pavilion was also fabricated at the same time of the COVID-19. So at the end, we use earth from Switzerland. And with earth, I want to mention something that is totally different. Like when you change your geographically location, you change absolutely everything with earth because you change the components. So in this case, we started to find these kind of failures that also it's an opportunity to study what is the most optimal mix to use the earth. And actually, this project we didn't finish together, and then while my master's degree, my partner, Edurne Morales, she continued this to study what is the most optimized mix in the earth construction. And then also when we are working with robotic fabrication, we have a limited space of working. So in this case, we also have to do a strategy to try to merge all the pieces together. And at the end, this is the final result made by Grammatica. And then for my master thesis, I did this fly ash waste recycle transformed to mineral foam. And for example, as a designers and architectures, we need to use a more optimized systems to construction as 3D printing, and also more friendly materials as mineral foam. So in this case, I put this in the table too, because in Mexico, we also use this kind of lattices to create this microclimate in between the interior and the exterior. So in this case, if you can see the image, it's super interesting because we only are using one element, that is the concrete block, to perform as everything, as the support of the bed, as the wall, as the window, as everything. So with digital fabrication, we can also transform these kind of elements and also try to perform as different things of necessities. So in this case, I did my master in different stages as design, material, and the fabrication method. In the fabrication method, I 3D print in 10 minutes, then I get dry these pieces in 48 hours, and then I sinterate in an oven. So this is how the 3D print with with mineral foam looks like before the firing process, and then this is after the firing process. If you can see, it looks like clay, but it's not a clay. This is a mineral foam, and then you can see also the bubbles in the material. So I use a 3D print, a robotic arm, a material extruder, and a printing bed. And at the end, I did this geometric matrix just to study what is the most optimal geometries to work with this material. I did more than 50 prototyping and different stages of strategies to 3D print. And my first objective was, how can I get the best quality of printing? So I played with my matrix about layer height, layer width, robot speed, foot rate, and the nozzle diameter. So then I found this. So as you can see in the image, the first picture, the first layers are splashing, but then after the layer 3, it started to expand because it's a foam. So I have to design with this condition because this is the material condition. And my second goal is how to get the maximum height. So in this case, I was at the beginning just printing the perimeter, and then I started to have a strategy to get different kind of infills. And at the end, also I realized that I cannot print outside my trajectory. And I compare all of the geometries in terms of weight, volume of material, and time of printing. And if you can see, the circle is the most optimized geometry. So I selected this as my final geometry, and then I started to assemble in different ways. And also, I realized something. If I don't flip these objects, I can get a wall application. If I flip it, I can get a screen. And then I started to study both architectural applications. The first one was the wall. But for the wall, I need 200 bricks. And this is how it looks like in an architectural space. And then for a screen, I just need 24 bricks. And this is also more optimized, so this is why I selected as my final prototype. And one of the interesting things about this material is super lightweight because the density is super low. So in this case, the final product is around 50 kilograms. So this is the final image in how I fabricate with this material. I also create this microclimate that we were talking about before, and this is the final result. So at the end, I get the goal about controlling the shadowing and the natural lighting. But I not only do digital projects with digital fabrication, I also work with Ensemble Studio, and I did this project that is called Domo Canvas. Domo Canvas is the furniture for this big pavilion that was in Montana in United States. In this case, I work with my hands, totally by hand. I knit these furnitures by myself alone as an Hermes bag, and then I also I use this kind of fabric made by concrete. So if you add water, then you can play with this kind of fabric, and then you can create very different wrinkles in the fabric. So I really love this image because I did these 3 outputs. So most of the people think I did the geometry first in the computer, and then I 3D printed, and again I did the rest. But no, like the real thing, I did the furniture first, and then thank you for 3D scanning and Grasshopper, I can get digital fabrication outputs as CNC milling or 3D printing. So, but I also asked, what happens if we do it in the other way around? So that's why we started our studio called Manufactura. Manufactura is also a studio founded by myself, Edurne Morales, and Eduardo Barba. And right now, what we are doing is this. We are merging the tradition and the innovation. Why? Because we believe in the use of technology for a sustainable future-built environment, building an innovative future based on tradition and developing dialogues between digital fabrication and humanity. We are located in Dr. Erazo in Colonia Doctores in Mexico City, and we have a robotic arm that which also allows us to work with different materials. So in this case, our material research is very local and traditional materials like local clays, earth, and ceramics, but also, on the other hand, we have a lot of recycled materials. So what is our services? We do additive manufacturing, also subtractive manufacturing, and automated manufacturing. So the first project I'm going to present is the actual project that we do in collaboration with Montserrat Ayala. The question is, it is possible to beat with our waste? The answer is yes. So we started to discover what we can do with the eggshell. Why eggshell? Because Mexico is the first producer of egg in the world and also the fourth consumer of eggshell. We always have egg in our diet, really present. So there is a lot of waste of this material in my country. So we also started to play what happened with this waste. So we started first to study the material by hand. To destroy it, we do a PLA cast, and then we just put this material to understand how this material behaves. After this, we digitalize this material to allow in the 3D printing. So we destroy this material in a really small pieces, then we sanitize it, and then we agglomerate with xanthan gum, a lot of organic agglomerants, and at the end, we got this. We got a really nice bioceramic that allow us to 3D print several pieces in our robotic arm. So this is a robotic arm, and with a ceramic extruder in a normal temperature, we are allowed to 3D print, and this is the result. So right now, also, it's very interesting, the 3D printing with eggshell, because if you can see, you can also see the material. You can also see the nature of the eggshell, and if you change the color of the eggshell, you change the color of the final pieces. And also, this is how it looks like before the drying system. And one of the interesting parts of this biocomposite, in comparison with ceramics, you don't need a firing process. With the normal temperature, you can get it dry and get it stressed and get the better structural performance. So also, we do geometrical studies about which one is the most optimal. At the end, we select this one and this structure and this size as the most optimal geometry and measurements to work with this material. So at the end, we do the first prototype made by 115 pieces, and we do a wall totally assembled by hand, but this wall also was designed for to be assembled each other to have a really good structural stability. So this is how the texture looks like now in the outside, and as I mentioned, this is the result of working with our waste. It's totally possible, and it's also super, very close to a normal ceramic. So this is the first prototype we do, and we expose this in Design Week Mexico 2022. And the second prototype we work with the same material is this column. This column was made by also a guest designer, Maria Pia Saf, and she was designing also a tower made by 3 towers connected by a computational design. Also, we were guessing what happened if we change the brick size, and what happened is also we changed the infill size in a very parametrical way. So this column was constructed by 30 pieces. All of them are totally different. So also this is the result of the material, and they assemble each other all over, one on top of the other one, and then at the end it's totally possible to build with our waste. Right now we are in a stage that we are studying the structural behaviors, and also we also want to bring this material as a construction material to be possible to be using in the construction sector. So I also want to present another project that we do. We also work with ceramics. In this case, we do these candles in collaboration with Amphora Studio and the New Sanctuaries. In this case, the client was doing a perfume and an exhibition to get a perfume. So she asked me, can the ceramic have a smell? The answer is no, ceramic cannot have a smell. But we use a plaster that is very common in Mexico called chucum, that it comes from the pre-Hispanic, our ancestor of vernacular material, that is a plaster that we added after the firing process to get the perfume inside these candles. So this is the exhibition that we made, and this is how the candles look like. And also digital fabrication allows us to have this kind of aesthetics, and we use the 3D printing with normal local ceramic, and after this, we fire these pieces, and then we add the chucum in top of this to get the smell. So our third project is Sueños with Earth and Concrete. We work with the MIT Digital Structures, HLA, and the New Story. In this case, we were doing a pavilion that was exhibited last year for Mextropoli Festival of Architecture in Mexico City. And in this case, we combine 3 different materials that is always using in affordable housing in Mexico. What is these materials? Compressed air blocks that made by HLR, the precast concrete that also, this precast concrete is super interesting because it was changing the shape for having a better structural performance. So in this case, what we did is the bovedillas. This system is named in Spanish bigueta and bovedilla that is super traditional used in Mexico. So in this case, because the precast beam, it was changing the shape, of course the beams was also changing the shape. So we have 18 different pieces, and then we repeat this 10 times. So at the end, we did it with digital fabrication and robotics, and we collaborate with Amphora to work with a really local material that came from two regions of Mexico. The one is the Oaxaca clay. Oaxaca clay gives the color and the texture, and the Zacatecas clay, it gives because it have a lot of sand, a lot of reinforcement and structure behavior. So at the end, this is how the beams look like before the firing process, and this is the final result. At the end, we have these beams that they are working together, and they have the super common terracotta color that everybody loves from Mexico. So at the end, this is the complete beam, and if you can see also, the geometry is started to be flat, and then to get more curvy, to get more structural performance. And at the end, we fabricated more than 200 pieces, and then we collocated in the pavilion by hand with the constructors. Then we build it, and this is the final result. A very nice roof made by a local material, but with digital fabrication and computational design. And this year, we developed the wood project that is also the same mix that we use with the egg, but now with a lot of sawdust. We collaborate with La Metropolitana, who they are a really big designers of furniture, and they are always working with wood. But they told us a very big issue that they have in their fabric. They have a lot of waste of sawdust. They produce more than 50 kilograms per machine per day. That is super unhealthy also for the workers to always smell in these sawdust, and they don't have idea what to do with this. So in this case, we work with salam, that is a species located in the southwest of Mexico, super traditional because it was used for the Maya tradition. And then we just also applying with the same mix of the eggshell to see if it works, and it's totally working. Like right now, we are allowed to 3D print this, and we fabricated like different kind of bricks, and also if you can see, this is how it looks like when it dried, and you can see the natural of the sawdust, no? This is the final geometries that we also fabricated, and also in the same process with the eggshell, we don't use an oven for this. We don't use a firing process. We also use the normal temperature, and also we put it on the sun for 24 hours to remove all fungi and all bacteria. So this is the final result. It was a really small facades using for an exposition, and it's totally also allowed to fabricate it with our waste. So I'm also teaching in Universidad Iberoamericana, and in this case with my students, we also research about what happens if we work with traditional ceramic, but with pigments also, how to get color to the ceramic. So in this case, we use this color that is Azul Colonial. This is the color from Amphora. We collaborate with them again, and it's the first time that I was trying also to pigment the ceramic, not after the printing, before the printing. So in this case, we studied like the area that we were working with, that is our studio, that is a really oak factory in Mexico. So my students started to study the side, they started to study all the edges. This is the first iteration they were planning. They were planning to do like a roof system, but at the end, this one was not working for 3D printing. So this is the final shapes. They started also to study and to have different kind of elements. In this case, they have different kinds of pieces, the A, the V, and the C family. And then with computational design, they do a grasshopper pattern, no, to accommodate this shape. And this one is the final result. They also started to play with the pigments, and I'm gonna start to explain how to add the pigments. So at the beginning, you have the normal clay, and then you add the pigments in different also intensities as deep blue, intermediate, and light material, no? Before doing the firing process, and then you knead them by hand for 20 minutes. And after this, we prepare, this is my students preparing all these bullets of 70 centimeters to get faster printing and also like fooling the material in the tube. And then we got it, a 3D printing blue ceramic made by a traditional clay from Mexico. And then this is how we let it dry for 24 hours. Then we let it dry in an electronic dryer. And then this picture is really amazing because this is how the color looks before the firing process, and this is after the firing process. The color gets super stressed, and then they get really hot. And also my students tested this, like if it's a roof system, they have to really work with. So this is the final result. And our last project that we did is this. It's called the Talavera project. Talavera is not ceramic. It's a really prehistorical and also ancestral kind of ceramics. It's from the family of the ceramics, but it came from Spain to Mexico in the like very old, when the Spanish conquered us. So it was also like showing the message from our cultures. And in this case, we want to also like involve innovation in a really protected and traditional method, that is the Talavera. Talavera is protected by the law. You cannot innovate this process. You cannot modify or replace this process because it's part of our cultural heritage. So the people in Urarte Talavera, that is the oldest house of Talavera production, they told us they have two issues. First of all, they cannot be allowed to innovate in any way. And the second, they have a lot of waste. Like, because the material is super protected by the law, they cannot sell it, they cannot use it, like after if one of the pieces get broken or they do not pass the control quality. So what they are mentioning, what we can do with this kind of waste? There is a lot of volume. So we try to, first of all, get from 3D printing ceramics, we get a piece, and then we remove the lines by hand, with a sponge and by hand. We do this because after this, an artisan made the mold in a very traditional plaster. So this is the plaster that they get, and then an artisan, a certificate artisan, because I cannot be part of this, then he molded by hand. And after this, Guadalupe, she's an artist, and then she refined all the pieces by hand. Then they get to glaze it, so this is how it looks like when the material gets glazed. And then another artisan finished it also totally by hand. And then the final step is this, the painting. But the painting is super interesting because it has to be totally by hand, every piece, each piece, and also with a pencil that came from a mule hair, because this is how the law of the culture in the heritage culture is set. So we painted this with a really traditional color that is azul cobalto or cobalt blue. So at the end, from a very industrial process that it could be the 3D printing and robotics, we also, with digital manufacturing, we do this. We merge and we have a conversation with the traditional fabrication, and this is the final result. This is the piece we fabricated, and we merged the innovation and the tradition in the same space. How we do it? We did this column made by 3D printing pieces, and then they replicated 80 times, and it means the innovation in Talavera process, but then we fill it with a really big carpet of waste because we want to also question in the people, we can also use our cultural heritage waste. Why we are protecting this? To create more volume or more problems to our environment? So this is the final result, and this is the pieces made totally by an artisan persons. And this one also was exposed in a really famous patio called the Uriarte House in Puebla, Mexico. So this is Manufactura. We always have a conversation with the machines. We always have connection with the materials that we work. We always are making new solutions or alternatives through technology to get a more sustainable environment. And we also create community with, for example, these indigenous people that they do not have connection with technology. So at the end, all our tools are made by Mexican manufacturing, and also it's not always like everything is digital. We also do some works after the printing by hand. So also I'm teaching in several universities to try to explain to my students how to relate it with the material, how to also have a criteria to work with. As a conclusion, I say digital fabrication is not a linear process. It's an infinite loop that is always fit by design fabrication through the material. So what happens when the people are no longer part of the construction? Digital fabrication have a lot of advantages. As you can see, new applications, opportunity to new construction process, use and experimentations of new materials, replicable process, and optimal management. But also have a lot of disadvantages of replacing of the loss of employment, loss of the human touch, changing the labor relationships as makes visible the inequality between our society. The European book said that in 2057, 2.7 million jobs will be replaced by robots. But Mexico have another condition. More than 60% of the national population are living in extreme poverty. Only 1% of the population represent more than our national GDP. Only 59% have access to internet, and the most important, more than 70% of the population are living in self-built houses. So why labor in Mexico is so cheap? The first thing is because educational lack, and then they have urgency to generate money. Only 4 out of 100 Mexicans have an income more than 50,000 pesos. So Mexico is a totally manufacturing country. Why? Because 6.9 people are engaged in labor force, but in a really risky conditions. So they work for more than 56 hours, and also in the Mexican companies, only the 93% use analog tools, and only the 6% use digital tools. So construction industry in Mexico represents the fourth largest economical sector in Mexico, and it's not being innovated. So robotic construction is not purely craft, it's political, it's cultural, it's economical, and it's social. This is an image about Cemex, presenting the first concrete 3D printing in Mexico. And what's the answer from the people? Los albañiles, disemployment, the workers, they're gonna remove my job. No, this is the answer from the people. So today, energy and raw materials costs are far from irrelevant. Labor costs will be increasingly affected by robotic automation. The question remains, can the revolution still be made by a printing costing more than $25,000? Today, we know these technologies are achievable, but all the social aspects and intellectual works start right now. Automation does not distinguish between design or manufacturing or even economics. They distinguish the obsolescence of the workflow. So my question is, what's the role of the robots in architecture? A robot, this is the European book said, a robot has to be able to work beyond human capability, doing the things that humans could not do effectively, and robots need to be able to make decisions autonomously. I really want to close with this image because this is an artist called Stellark, and he said, there is no more human thing than technology. Why? Because technology has the shape of the human body, and they allow us to get evolution of our species. I did this exercise with my students, and they selected one architectural item. I told them, build someone totally by hand, and then the other one totally automated, and tell me which one is more difficult or complex. So at the end, they told me, working by hand, it was more difficult than working with a robot because they never have a contact with their body, with the material. But that communication with the robot is also a very complex stage. So as Mario Carpo said in his book, Beyond Bending, technology should not replace human contact. There cannot be a community without a physical proximity. So robots have a lot of advantages of optimizing process, precisely, a really good different kind of designs, but also human contact have the most important thing, that is intuition. It's never clear when a human starts and a human ends. Thank you so much.
Thank you so much. We're running a little bit behind, so I'll hand it off to Nadia.
Thank you very much to our first speakers and to Tiffany for the moderation. We will now have a 10 minutes coffee break. You can help yourselves to the table over there. And then we'll resume with our second session, computational design. Thank you.
Just to check if the video works or something.
That's it. Yeah, I think I already have it. I have to check what I already downloaded it.
and the production of concrete, the largest cost associated with the production of concrete structures and components relates to the formwork. So it's not only about reducing the material use of concrete itself during production, but also thinking about how can we bypass entirely or mostly formwork, or if we do use formwork, how can formwork be circular. So we had 3 declared aims. It's very weird that the font changed in terms of the numbering. So the first one was a circular approach towards formwork, where we were focusing on the robotic shaping of sand. The second aim, developing computational design strategies and 3D concrete printing of lattice-based screen components for both interior and exterior use, and an investigation into the ornamental qualities of concrete via additive manufacturing. Since we were focusing on sand in terms of the formwork here, you can find a lot of historic references and precedents in terms of that. So here is a selected one of sand formwork that was used for precast concrete panels for the Philips Pavilion that was developed by Le Corbusier and Yannis Xenakis for the World Expo in Brussels. Simultaneously, as shown on the render beforehand, we were really interested in this quality of the concrete, using concrete as a screen, which you normally wouldn't do, right? So concrete would rather think of it in terms of its structural purposes or structurally use to transform the space where it's in. Here, due to the fabrication process, these type of depicted components of the screen, right, they're planar. So what we tried to do is to develop double curved facade lenses out of concrete. In the very early start, we focused on the robotic sand shaping itself, testing and developing a series of end effectors for the shaping of the sand and trying to understand its behavior. We were working at room temperature and room humidity, and what we very quickly realized is that we could really be in control of the sand shaping also without adding any further additives to the sand or adding any further water. We did try experiments with spraying water on the sand, but no significant quality in terms of the surface resolution was detected. Then trying also to shape, as you saw beforehand, double curved surfaces, and then developing a strategy and an end effector where we were using this 6 horizontal oval planes to shape the sand. Overall, the sand shaping was quite fast, so to achieve the type of resolution that we needed for the sand, that was done in cycles of in 5 cycles of shaping of shaping the sand. And here you can see also our robotic setup. So we opted for dynamic movement of the robot on the tracks in order to avoid singularity and an over-rotation of the joints. The second step then was focusing on the differential growth algorithm that was selected purely for the fact that we wouldn't have any points of intersection and we could do very easily continuous printing path. We printed the first layer was always printed at the same speed with a differentiation strategy, which I'm going to talk about for the subsequent layers, and we printed up to 5 layers of the concrete. Here you can see one more time the concrete, the robotic setup and the printing. Initial testing was done first with printing, orientating the nozzle at 90 degrees towards the ground plane. There we could detect that due to this orientation, the layers of concrete, particularly the first layer of concrete was slightly sliding off the sand, which then was problematic in terms of the position of the subsequent 2nd, 3rd, 4th and 5th layer, opting then for printing perpendicularly to the sand surface itself. We were following a material depositing strategy where we would differentiate between the different layer width while printing, and this was really done via the printing speed. So we developed a Vertigo also due to prior testing and collaboration with Sumum Engineering. They developed an algorithm where you could really coordinate this and control it during the printing process. Then trying out also different types of openings and printing also, whereas first tests were done without printing a frame, then subsequent tests also with building a frame for future anchoring within a larger constructive system. Generally, depending of course on the number of printed layers, one of the components has a weight between roughly 17 to 22, 23 kilograms, and you can see also the shadow effect that we reached on the ground. In terms of the future steps, we're looking now into optimal reinforcement strategies for the filigrees themselves. A more further differentiated material depositing strategy according to a structural analysis, and defining or refining the interface with building components and the development of connection details to this building components. Right, very quickly now an overview of further research that we're undertaking. We moved in the last 2 years into 3D clay printing. We are using the WAS printer there that you can see, doing all sorts of different experiments with different type of pigments, trying different types of freeforms, and focusing right now on facade systems. You can see also some fails. I think due to time constraints, I'm just going to go a teeny tiny bit faster through it. Here where we use the Turing pattern to develop a facade system, a tiling system, that you can see also downstairs exhibited as part of the exhibition. Testing also different types of glazing, understanding how deformation and warping are correlated to the different burning, to the different firing temperatures, and how these can be minimized. And here also the second facade system that is also exhibited downstairs, looking into folding behavior of textiles and how this can be translated into clay, and different type of knitting patterns also translated into clay. And currently we're working on this installation that is both a wall system and also a floating structure. That is it. Session with our first speaker, which is Professor Christian Lauter. And just a quick introduction to Professor Lauter. So his research and the research of the group of structural design and building engineering at the TU Delft focuses on the development of novel methods and strategies for the design and construction of safe, smart, and sustainable structures. Their research includes thematic areas such as structural safety, digital design production, and sustainable design and construction. Thank you very much, and welcome.
Okay, good afternoon. My name is Christian Lauter, Professor of Structural Design and Building Engineering at TU Delft. And I'm happy to be here together with my colleague Daniel Pfarr, who is a researcher at the Institute of Building Construction at TU Dresden. And today we want to show you our research about thin glass composites with a 3D printed core pattern. This is just a small example or a small sample of it. The idea is that we combine very strong thin glass to make a very lightweight and strong composite panel that we intend to use as a facade, or perhaps as a roof, or even you could think about a floor system. And the benefit is that you use much less material than conventional glass, as you see here in the building today. And that you can also optimize or customize your pattern that you see in between the glass. Just as a short outline, we present a little bit about the concept of it, the upscaling, the performance, a short outlook into what will be the next step, and then we close it up. So first of all, the concept. So how did we come to this idea? It started all with thinking about how you can use thin glass, and then I refer to the glass that you have on your devices, your mobile phone or your tablet, which is in the range of 0.1 to 2 millimeters, let's say. And it's very strong because it has been chemically strengthened, so 10 times stronger than regular glass, more or less. And it's also very flexible, so you can easily flex the glass in desired curvatures. So this is a piece of thin glass, and you can see that you can easily bend it into desired curvatures, so by hand, by cold bending, we call that. Many people think it's plastic, but it's really glass, actually. Here you can see a small test on 2 millimeter glass, so actually in the thicker range, I would say. So we do some column buckling by pressing it downwards, and you can see the glass quite bending outwards. We have a strain gauge on there to measure the strain and calculate the stress from that, to see how far we can bend it before it fractures. And then it slows down the video, because we arrive at the full fracture. Just one disclaimer, it explodes quite explosively, because there's a lot of strain energy in the glass. If I would drop this piece of glass, it will fracture in big pieces, so a bit safer than this. But now we have so much build-up energy that once it breaks, it's exploding in all directions. So very strong thin glass. Here you can see a plot of it. We reach strength values of well over 400 megapascals. And actually in this setup, it failed from the clamp. So we could push it much further, but we had to improve the setup for that. And then you can get to 800 or 900 megapascals, which is, let's say, in the range of high-strength steels. So we had a series of master students looking into what can you do with it. So first concept was to look into adaptive facades. So on the right-hand side, you see a shape memory alloy activated thin glass facade that opens up. So by pulling up this bar in the middle, you will open up your facade for ventilation when it's too hot, and then when it has cooled down, then it closes automatically again. And this makes use of the flexibility of the thin glass. But then other concept that we would like to talk about today is more to combine the thin glass with a core pattern to stiffen the glass, because you can imagine that this vibration is too much for a building. It's causing noises, it's causing too much deformation and too much nuisance for building occupants. So we thought about combining it with more conventional, on the left-hand side, closed cell or honeycomb kind of patterns, but also perhaps with open cell configurations. And there the idea came also to print those patterns. And the first student looked into that to print a truss structure. That's what you see here, so that you have a pattern that is stiffening the thin glass for that, and that you create this very lightweight thin glass facade panel. Of course, we tested that in a very small scale, really A4 scale, and luckily also it worked with our analytical model, so it combined very well. And then we had next steps in a student looking into can you use Voronoi optimization there or tessellation there to create perhaps a bit more structurally optimized pattern. And at the same time, you can imagine that you have now viewing zones in your glass that you can look through, and you also have zones which are blocking the sun and provide a bit of shading there. So he made quite some nice samples there. Some of these are also passing around in the audience. And he also proposed a nice design of how to implement that in a building or a roof or a facade. And then optimizing your core pattern for structural, but also for daylighting purposes, that you can really regulate how much light you can get into your building. And the next step was to look into, since the glass is easily bendable, can we also exploit that to make curved 3D printed patterns and then glue the glass easily on top of that, And you don't need any heat or something to bend the glass, so you can easily bend it, let's say, by hand and make these small-scale curved composite panels. Then for a while I moved to TU Dresden for 3 years as a professor of building construction, where I met Daniel first as a master's student and later as a researcher PhD student. And one of the focus there was to really upscale this concept. So we looked into how can we make it bigger. And the first idea was to stitch smaller prints together, which of course worked well, but it was still quite labor intensive. And Daniel devised a very nice interlocking scheme that you can stitch such smaller panels together. At the same time, of course, it's not shifting. Yeah. At the same time, of course, there was the challenge of gluing. So we are gluing the thin glass to the pattern, which was done manually at that time. And of course, there we also wanted to see if we can automate that process and be more efficient there. So the whole question was about how do we get from a small-scale A4-sized panel to a big-scale panel. And we saw no other option than to apply for a significant grant or significant fund to buy a large robotic 3D printer. And luckily we got the grant. So here you see a 4x2 meter print bed, which can be heated, and the robotic extruder there, or the robotic operated extruder there, to be able to print our facade scale kind of patterns. So how do we do it? So we can print different kinds of polymers, either with or without glass fiber reinforcement in there, or opaque or also a bit more translucent. And we prefer to print on a flat piece. So here we're printing on aluminum, which is heated then from the bottom by the heated bed. But later you also see that we print on glass directly to have a very smooth surface to be able to glue to. And then in the next step, we grind the top surface. So the top surface is milled off, also robotically, just to be able to get a perfectly smooth surface again to be able to glue on it. And that gluing is then done in the next step by this also robotically operated reservoir, let's say, applying the glue with specific pressure and specific speed. And this glue is UV curing, so it's only getting rigid, let's say, if you apply UV light from the sun or from an artificial light. So until that point that you apply the light, you can still maneuver and you can still take your time to apply the adhesive, let's say. Another thing is that this adhesive is very thin normally, less than 1 millimeter, so you don't have that much tolerances to compensate, or not that much capacity to compensate for tolerances. That's why we really want to mill it down to have a smooth surface for the gluing. And later you will see also Daniel will show a bit more about hot melt adhesive, which are a bit more tolerant in terms of sizing. And then we come to the assembly. So here you see the robot still applying the glue, and on the right hand side you see the thin glass being laid down by suction cups already, ready to be moved on top of the adhesive there. Now it's there, and then the next step would be to illuminate the adhesive with UV light. So following these 4 steps of additive manufacturing of the core, then to mill down the core to facilitate adhesive bonding, and then adhesive bonding and the assembly. That's our process to come to really large scale or full scale facade prototypes that we can then also test in the lab. And there comes in the research of Daniel, who is looking into the design and the performance of such panels.
Yes, thank you very much for having me here as well. Yeah, when it comes to performance, we can of course talk about different objectives or different categories. Today I want to give a brief introduction into some mechanical properties at first. And because we want to achieve a facade element, so the idea is very close to test it in a wind load test. Therefore, we have a big facade testing wall at our laboratory in Dresden. You can see here already in the to the right-hand side the
the test specimen, which is built into the facade test wall. On the left picture, that's the technical drawing. That was already only a preliminary test at first. Dimensions from roundabout almost 2 meter by 1 meter in size. And you can see the honeycomb structure, which is 14 millimeter thick. It was a PETG-based polymer with 20% glass fiber. And on the top, on each side, we glued a still 3 millimeter thick, I would say, glass sheet on it. And yes, the whole test specimen was supported on each side. And we can blow in and suck out air into the cavity behind the facade element. And yeah, we test the element until 4,000 Pascal, which is still quite a lot. So if you would want to calculate the facade panel, you would estimate in Germany, as far as I know, 1,500 Pascals. So it is a really strong wind load on this panel. And we tried to measure everything with the DIC system, with the digital image correlation system, so that we get some deformation and displacements from the panel when it is loaded. And when we look into evaluation, we compared two different systems. So in the top or in the bottom part of the picture, you see the DIC picture. So that is the actual deformation of the panel during the loading. And on the top, there's a finite element simulation, which represents the physical tests quite well. And we measured at the maximum load of 4,000 Pascals, only 2.3 millimeters deformation. And just to compare it a little bit to other structures or glass structures, that would be the same or roughly the same deformation which you would get when you have a 12 millimeter monolithic glass pane, so one solid glass pane. And that already means that we save 50% of the glass used, and we only have 40% less weight, because we are adding a little bit of weight during the additive manufacturing process. Another example to compare it with is an IGU, so an insulating glass unit that is probably more common, like you see here in the facade as well. There you have a 10 millimeter glass sheet outside, a 16 millimeter cavity filled with air or the different gas, and an 8 millimeter glass sheet in the inner side, and that would mean already 70% less glass and 65% less weight. And in our current project, we are investigating, okay, what impact can we expect to CO2 emissions or other environmental aspects. And therefore, we have a test facade or an example, which is a building in Dresden that is kind of a conference center, or our students have their lectures there. And only this facade, what you can see here in the picture, is 300 square meters of glass, which means already 30 tons of glass. And only the production of this glass would make 20 tons of CO2 equivalents. And so our idea is basically to not only reduce the mass in the building, but also reducing the material from this energy-intensive glass. And so switching from the left side, from the traditional IGU, to a right side, to a composite panel with only 2 millimeters glass on each side. And there we can expect a lot of reduction in weight and CO2 emissions.
Yeah, so far we have mostly looked at the structural performance of the panels, but also thermal performance is an issue, of course, that we need to have a closer look into. On these images, you can see some models of the thermal model, let's say, and you can see that we are losing heat at some points, and that's where you expect where the core is touching the glass, let's say. So there we see some thermal bridging happening, of course, because normally an IGU or insulating glass panel doesn't have this core inside. But now with the blue core that I drafted there, you see that there's a thermal bridge coming from the left to the right-hand side of the glass, so bringing your heat or your cold to the other side of the panel, which we would like to prevent, of course. I cannot point with this computer, but the idea is then to perhaps to apply a second layer, as you also see now with triple IGU, triple insulating glass, and make sure that the cores in these two individual chambers don't touch. so that you don't have direct conduction there. Or simply apply an extra layer with a cavity which is empty, which can still benefit actually from the stiffness of the other panel. But in this case, you avoid this thermal bridge from inside to outside. And the other option is to separate the core, let's say, to make two cores, to print them on either side of the glass panel, so that you avoid that this core is bridging from the one to the other glass. And another issue that we would like to look into a bit more later is also daylight control. Of course, this panel can be optimized for structural purposes, but also for daylight control purposes. So having more pattern where you would like to block the light, incoming light, and having a more open pattern when you would like to have the view or the light in. And perhaps also to use the curvature or the angle of the pattern to reflect light inwards or to the ceiling as you wish. So here you can see some render on the left-hand side, but also you can see that the shading already indicates a little bit of what you can achieve in this respect.
Yes, then let's come back a little bit to 3D printing again. What we are looking right now is actually to go to curved panels. We have the robotic arm, we have the thin glass, which is very flexible, so we want to make use of it. We have the potential of computational design to design in a variety of geometries. And so the next idea is to go for curved panels, and therefore we need design procedures, production procedures, which can be automatic, which can be automatically. And so here on the left side you can see rendering how we could design a panel like that. So we are directly designing the print path, which is expected later on with the robot. And then we are projecting it to some kind of free form which represents the facade. And on the right hand you can directly see it doesn't matter which panel you are choosing, the print path is directly generated, and we can transport it or we can give it to the robot and it will additive manufacture the core structure. And there's also included that the gluing after the printing or the milling process if needed. And so we want to have a file to factory process which is almost digitally until you come to the real printing. How we start with that is that we just milled out these kind of formwork. So that's the wooden formwork, which is as well parametric designed, so we can easily change it, and it is quite low cost to produce it. So that is, for example, the milling process, which is needed then to get the shapes, and then we just simply put the wooden blades together once we have changed the shape of them. Yes, and then we have a curved surface which we can print on. You can here see a very thin sheet of glass, so this is only 0.7 millimeters thick. We can heat it from below, and then we can directly print on the curved surface. And we have a curved core structure. And the next step is to glue it somehow, and therefore we already heard about the acrylic, which is UV hardening, but it's very like honey, so when you have a curved surface it will flow down to a certain point. So we are investigating new methods to glue it. One promising example could be the hot melt, which we are using here. So we just mounted a hot melt glue gun on the left side to our robot, and then we took the same way like the last layer of printing, and so we are applying the hot melt. That is totally fine when it's cooled down, because then we go to a second lamination process where we stack up the glass with the core structure, and then we put it into the oven, and then we are laminating the core and the print together. Yes, and some closing words then again.
Yeah, so we come to the end of the presentation. Still a lot of work to do in the next years, I think, but we would like to convey the message that we're working on strong and stiff, yet very lightweight facade panels or floor panels or roof panels, which have less embodied energy than conventional facades. And you can also optimize the pattern according to your performances or also do your architectural intent, let's say. This presentation is short. You can read more in the Beam booklet, or in the meantime, you can also look at one of our recent journal papers published with Springer in the Architecture, Structure and Construction Material journal. Sorry. And we would like to thank very much the funds that we have obtained for the printer itself on the left-hand side, but also for continuing in a project with several partners at TU Dresden that is looking more into the real implementation of such components in facades. And we would like to thank you very much for your attention.
Thank you very much for the wonderful presentation and the projects. Do we have any questions from the audience?
Thank you for the presentation. I have a question. Am I understand right that the usage of glass with ultraviolet protection is not possible because of gluing process?
Yeah, you mean that if you have any UV blocking mechanism, that it would be difficult to use the UV curing glue. I think to a certain extent that's valid, especially if you come to a laminated glass. But at the hot melt that Daniel showed in the end doesn't have this UV activation need. So that's heated, or that's cured by heat in the end.
Okay. And for the second possibility to for adhesive assembly, so it means last layer is not hot all the time. So glass will be put on top and then it will be made. So you bring heat again.
Yes, so we first 3D print the core structure, then we take off the 3D printed core, and then we can put it back to apply the adhesive. Then we flip it around to put the adhesive on the other side of the core element, and then we have a core structure with two-sided hot melt, which is cooled down. Then we can stack the glass on it. We put it in a vacuum bag because we want to achieve the curvature as well, so it is pressed down to the adhesive, and then it comes to an oven at 120 degrees, for example. And then the hot melt is melting and it's reconnecting, and then it's connecting the core structure with the glass. So it's a second step after the printing.
Thank you.
Welcome.
Thank you very much. Do we have any further questions? Sorry.
Thanks for the presentation. I had a question if you have looked into the full life cycle, because I guess you can't get around this topic these days anymore, and if you have looked into this, how to recycle or what to do with the product once it's not needed anymore, because the glass only, I guess you could recycle, and then there's plastic glued onto it.
Yes, a very good question. That is a big part of our current research project, which is now running for 1 year, and so we still have 2 years left. So at first we looked into the A module of the building cycle, so only the production of the materials and the CO2 emissions during production. The next one will be the living phase. So now we have to care about U values and performance in terms of thermal insulation and things like that. And we go the full circle until the D level, and we want to, or we make concepts how to recycle it. The UV hardening acrylic is very challenging to recycle because that is like, the bond is very strong and we can't really disassemble the whole product. The hot melt is a little bit more beneficial because we can just heat it up to 90 or 100 degrees and then we can take it off, so that's the idea. But yes, we're still working on concepts how to completely disassemble the whole product, but that's a little bit way to go still.
Wonderful. Thank you very much for the lovely presentation. We are going to then go to the next presenter, since I have been asked to be really strict with timekeeping. Right.
And Our next presenter is Matilde Marengo. She is the Head of Studies, Faculty and PhD Supervisor at the Institute for Advanced Architecture of Catalonia, IA. Her research focuses on the contemporary urban phenomenon, its integration with technology, and its implications on the future of our planet. Within today's critical environment, a social and economic framework, Matilde investigates the responsibility of designers in answering these challenges through circular and metabolic design. Thank you very much, Matilde, and looking forward to your presentation.
Thank you very much. Thank you, Nadja, and the team for inviting me and organizing this fantastic event. So as Christina said, I'm Matilde. I'm Head of Studies at IAC. I will make a small disclaimer. I am an architect and my PhD is in urban design, so maybe I'm coming at additive manufacturing from a slightly different perspective than some of the other talks that we've heard earlier today. But I wanted to talk to you a little bit about the research that we've been doing at IAC in relation to additive manufacturing, and in particular how we've been using that to create or innovate within the context of performative, inclusive, and resilient design for built environments. So firstly, just if some of you are not familiar with IAC, we are a research, education, and digital fabrication center, and we're based in Barcelona. The institute is dedicated, it's quite a young institute, and we're dedicated to shaping the future habitat for our society. And what's really important is that we're dedicated to building it within the present context. Our activities are intrinsically related or intersected one within the other. So we're working with research within education, within development, and within promotion, with the idea of breaking down the boundaries between these different sectors and really creating a synergy between the practice or the professional realm and the realm of research and education. And we do this in order to be able to follow the digital revolution at all scales and push the boundaries of fundamentally architecture and cities in order to be able to meet the challenges that we face as humanity today. So I'm going to talk to you a little bit about the research that we've been doing in 3D printing architecture with Earth. It's a 10-year research journey, which in this presentation will culminate with a project called TOVA, and then I'll have one last little project on the end. But fundamentally, our work centers around this idea of negotiating between machine, design, and material. So fundamentally looking at not just the negotiation between the machine and the material, sort of developing new processes, new tools, in order to be able to sort of manage this situation, but also the negotiation of design from different perspectives, so from the design of the object, the design of the material according to the performances that we're after, the design of the section of the wall, but also the design of the architecture and the larger scale of the architecture within its context in the built environment. As Christina was saying earlier, so I don't repeat it, obviously our intention is to sort of face some of the larger scale challenges that we have within the context of the built environment and give a response to these in some way. So we started our journey in 3D printing architecture with clay in 2012. Actually, Christina was at IAC at that time working on another project that focused more on the technology of 3D printing. But in parallel, there was research being developed called Pylos, which actually means clay or earth, if I'm not wrong, in Greek, and looking at developing a series of material recipes that would enable us to be able to 3D print with clay. So fundamentally, this research has been ongoing since the initial start of it, working with different mixes of clay, and as I think Dinora mentioned before, clay is different everywhere you find it, so obviously you need to adapt your earth mix or your mix for 3D printing to the specificities of the local clay. But we've been working with different aggregates, water, bio-based additives, and obviously mineral additives in order to create a material that can enable us to control its viscosity, the stickiness of the material, the capacity to absorb water of the material, the drying period of the material, and finally have some data and information on how the material will shrink once it is in fact printed. Further to this, obviously we have identified the need in some way to be able to integrate feedback loops. Can I hide the meeting panels? No? Okay, no pasa nada. Sorry. Integrate feedback loops between the material itself, the material that's being printed, to be able to understand through the printing process what it is that we can control and what do we have to do within that process. So specifically in one of the projects that we worked in on-site construction, which was actually a pavilion printed, you can see it on the left-hand side of your screen, a pavilion printed out in one of the construction fairs in Barcelona called Construmat. We were working with drones in order to be able to capture data and optimize the printing process within the actual printing period. So understanding the behavior of the material according to obviously the environmental factors that impact the material's behavior in itself during the printing process, and obviously to avoid any construction issues, among which buckling. From that project, we actually developed digital Adobe, which is the project once again on the left. This was a 5-meter high wall that was printed in different pieces and then assembled on site. This was actually also another challenge. So when working with earth, we're also interested in working with earthen materials in order to be able to ensure its biodegradability, but also its, that it's a truly biodegradable material, but also that it has the capacity to be recycled. So the pavilion that you saw previously that was developed in Construmat, on-site construction, was actually crushed. And we use that same material to build digital Adobe. So we do have, in some way, the proof that we can actually crumble the material, crush it, remix it, and reuse it for other projects, which is quite an important feat for us. Here, within the context of digital Adobe, we're not just using the recycling of demolition waste, but we're looking once again at the capacity to optimize the infill, the space within the wall spaces, and also the exterior facade, in order for it to be able to have certain characteristics of performance, whether that be thermal performance or environmental performance on the architectural scale. Some other elements that we've been since researching is how we can integrate perforations. Obviously, when working with clay and additive manufacturing in a layer-by-layer process, we have the difficulty of how we integrate perforations, how we integrate openings within the architectural form. So one of the challenges that we've been working on is understanding how we can do that in different ways, from working with micro openings to small wind-catching openings, or medium windows and large passages or doors. In order to be able to do this, we've been working a lot on understanding what is the overhang that we can work with in the layer-by-layer deposition with clay without having to have any formwork, and how we can integrate that into the construction process and the design process within the system. So in the bottom, you can see in the center bottom, you can see some of the tests where we're really pushing it to an extreme, taking data and taking information on that and integrating that into our design processes. As I was saying also, we have a series of needs to, on one side, integrate openings, but also we have the question of the fifth facade. So how do we close or how do we seal off our 3D printed systems? We have been working over the past couple of years also at looking at vernacular processes or vernacular architecture to gain some inspiration. In particular here, the inspiration from vaulted systems. Working with this and understanding once again what is the limit of the overhang that we can work with when working with layer by layer, and what are the integrations within the design system, such as ribs or buttress systems that we need to integrate in order to be able to ensure a structurally sound system. And finally, if we really want to push that, how we can integrate potentially formwork systems in order to push the limit of this cantilever of the layers, and work beyond what the material would be accepting. Here we're working on the use of formwork that is designed to be installed during the printing process and uninstalled, so in some way recyclable formwork, and the potential of working with a combination of wood and earth, so the negotiation between the different natural materials and how that would impact the actual architecture in itself. With all of this, we have a series of, let's say, outputs or considerations that we work with on the architectural scale of design, from choosing the geometry to a certain set of structural desires in order to foment or push the design. So from inertia, global and local inertia, inclination, and a series of questions of mass. All of this is oriented to, in some way, being able to adapt the specificities of the architecture to the micro-local context of the architecture. So we are working with additive manufacturing, which is a form of digital fabrication. We have the possibility to customize, really, the architecture, the shape, the form, to the necessities and the specificities of each specific location of the elements. So we work with the idea that the walls can all be different and respond to very localized conditions. Among some of these performances, we work with the question of heat conductivity. So obviously, clay in that sense is a very interesting material to work with thermal considerations. We also work with airflow as a design driver. And finally, also, of course, with water flow and understanding how we can sort of integrate different elements within the design system in order to be able to capture, leverage, or protect the building accordingly. The last and not least, of course, the architecture and the spaces that we design are designed to interact with humans. So we have been looking also at how we can integrate different systems that are necessary in some way and integrate ergonomics as a design driver also. So all of this culminates in the project, in the development of a series of architectural projects. So in parallel to working with, as I was saying, these design negotiations, or the negotiation, of design between material and machine, we're also looking at what this means, how do we scale this up, and what could this mean in different contexts, of course. So how can we adapt this material system to different specific contexts? So here we have a series of images that can give some ideas or visions of how that might be. But I want to take you to one specific project, which is a project called TOVA. Of course, as I was saying before, and as Christina mentioned, one of the questions that is very interesting when working with clay is the possibility to really create an entirely on-site process, and really working with not just 0 kilometer material, but almost 0 meter material. So how we can embed resiliency, but also very, very localized processes into the actual construction site. So with this feat or this challenge in mind, we started developing TOVA, which is a project, a prototype, developed by our researchers and also the students of the 3D printing architecture postgraduate program that we run at IAC. This is the actual project where you can see from the foundation material to the wall systems, to the integration of other systems such as wood and the roofing system. So this is in some way a culmination of all of the steps that I showed you previously in the presentation. This is the final picture of TOVA. So TOVA will be turning 2 in February. She's a February baby just like me. And so I invite you all to come visit TOVA in Barcelona. TOVA, here you can see on one side, and here on the other side, as you can see, we're looking at adapting the design. I will play, of course, and all of this is designed fundamentally. This is here in our Valdaura campus, which I will explain a little bit more about now. But fundamentally, all of this is designed in order to create visions, again, for an architectural scaling up or an understanding of how these methods could become replicable. So if the video works, we will play the video of TOVA. Okay, so this here is our Valdaura labs. We are very lucky to have a campus just 20 minutes away from the center of Barcelona in the Collserola Natural Park. So here we built Tova, also Digital Adobe, and some of the other prototypes that I was showing you before. This is basically the extraction of the clay material, and here we have the mix of the sincel fiber, enzymes, and water in order to be able to produce the material mix that we were working with. This project is a collaboration with WASP, so we used the WASP 3D printer in order to be able to print this out. And the printing process took, I think, just over a month, if I'm not wrong. So once again, here we see the different steps that I was discussing previously in the presentation, from optimizing the shapes of the walls for certain performances, from heat, thermal performances, but also the integration of ergonomic conditions. We also have the integration of a roofing system, which works with timber, locally sourced timber, of course. And fundamentally, what we're doing here with Tova is in some way attempting to respond to some of these challenges. There was a huge team that made this project possible, so of course, huge thanks to them as well. Let's see if I can go forwards now. Okay. Sorry. A little bit of happiness to share with you. Tova recently won one of the New European Bauhaus prizes for 2023 in the Shaping Circular Industrial Ecosystem and Supporting Life Cycle Thinking category. So it was one of the top 5 projects and one in the strand of champions. It was also selected as the I think best house or best living unit on the Spanish Art Daily platform, which was also really nice. So that's a public voting, so that's a great feat for us there. And just to close, I wanted to take you through another project, which also is based around 3D printing, looking at this time inclusive design strategies. So the project is Comida. It's a project that was funded by BitHabitat, which is a local funding scheme or an agency that provides local funding schemes in Barcelona. Comida is the implementation of a 3D printed wall system that is co-designed. It's been co-designed together with the citizens of 2 specific spaces. One is Connect Art and one is Passage de Trullas. Both of these spaces are spaces in Barcelona that are run by collectives. And fundamentally, Comida is designed in order to be able to host plants, plants that have different benefits, of course, integrating nature-based solutions into the 3D printed system, but also has the capacity to generate biophotovoltaic energy. So here is Comida. Comida is a modular system. And this is my beautiful colleague, Chiara. As you can see, this system is designed, as I was saying, to host plants, growing food producing plants, but also hosting many different species. So looking at, once again, the opportunity or the possibility of working with more than human design. So integrated into the Comida wall system, we have a series of spaces that can host birds and bats, but also insects. And finally, we have a series of cultivation spaces or spaces that are designed to host microbiota. Last but not least, we have a management system integrated. So Comida, as I was saying, has the capacity to produce biophotovoltaic energy. So fundamentally, the plants, when placed in soil, produce bacteria in their roots when they go through the photosynthesis process. And by integrating an anode and a cathode within these different modular systems, we have the capacity to capture these these bacteria in the form of electrons. As you can see here, the vases have different topographies or surface finishings according to their specific location on the wall and designed in order to host certain microbiota. With the energy that we are able to produce, we power our sensing system on the wall system, and we are able to capture some information, including, for example, the temperature, but also the humidity of the top vases to understand when we need to activate the watering system. This is a picture, a more recent picture. So here you can see that already the system is changing color, is capturing a little bit more of the,
let's say, biological matter that is growing around. Of course, on an urban scale or on a larger design scale, this brings the question of what we can do with the different blank facade systems that we have around our urban environment, and how we might be able to reimagine these. Also leveraging smaller scale systems in order to foment, for example, large scale ecological connectivity within our urban environments. And just to close, I will play a little video of Comida. Yeah, maybe? Yes. Okay, so Comida once again looks at responding to the challenge of our urban environment and how we can integrate living systems or natural systems within those. The wall was designed, parametrically optimized and shaped in order to be able to host more than human necessities. We 3D printed the modules out at IAC, and they are done in clay. The clay has not been glazed on purpose. This time the clay is fired, whereas in the other houses the clay was not fired. And fundamentally, this is in order for it to become a host for biological matter. The system or the use of 3D printing, of course, allows us to minimize the waste that we generate in the production of the wall system. And here we collaborated with Cumeia Cerâmica. Tony Cumeia is the owner of the Cumeia Cerâmica company. And as I was saying, we have a diversity of design of the different modules. So according to the requirements or the microclimatic conditions of the wall system, we can adapt the placing of these elements. It's, again, embedded with a biophotovoltaic system. And the process was all co-designed together with the users of the spaces of both, as I was saying, Connect Ort and Passage de Troyes. Here the setup of the modular system, which hangs off a structure. And we have a web app and a Telegram API that allows us to sort of interact with users, but also collect and share data. This is the co-design process, working with the users of the space. And fundamentally, the idea is that, as I was saying before, we discuss a little bit what are the potentials of the built environment and how we can integrate a diversity of systems within our architectural form. And with that, I would like to thank you for your attention. I'd also like to take the time to thank my colleagues. Of course, these are all incredibly collaborative efforts, so huge kudos to them. Thank you.
Thank you very much, Matilda, for the wonderful presentation. Do you have any questions from the audience?
Hello.
Hello.
Thank you very much. Very nice presentation and very amazing project. I'm really curious about this clay project because clay is really difficult to handle with. First, the shrinkage. Like, did you measure like how much is shrinkage of your object? And then I saw it's a hollow things, and I'm also curious about how you dry the inside of the hollow, because sometimes, like most of the time, when the one is outside is dried first and then the inside is still wet, it will cracks out of it. And then, yeah, so what is the strategy of avoid the crack? So is there any cracks in your project? And did you print it in the contained environment? Because I didn't really see it. Is it outside? And then...
I hope I remember all these questions.
Yeah, yes, that's true. Thank you.
Okay, no, thank you. So shrinkage, yeah, we've been measuring shrinkage since the beginning of the research. It's actually one of the input design parameters. So from the smaller scale tests, we have that as an input. So we have data that we've been collecting over the last 11 years. With regards to printing, the TOVA project was printed outside, on site with the WASP crane printer. We are constantly collecting feedback. So in an earlier slide in the presentation, I showed on-site construction where we had integrated sensor feedback systems in order to be able to capture information on how, for example, how dry the clay was before starting to add layers. So we have a constant feedback between the actual process of construction and the inputs of the construction in itself. So that allows us to capture this information. It's true that it dries faster on the inside, but it's also true that we built TOVA in the wintertime, so a very, very humid moment in general in Barcelona, and that creates a kind of condition where the environment is quite homogeneous, let's say, between the inside and the outside of the wall. Of course, if we were printing in the summer, it would be a completely different situation. We do have some projects were printed in AJAC, so like inside our facility. And of course, the on-site construction was printed in the construction fair in Barcelona. So those are like different, but always with this integration of feedback.
I would have one question, Matilda. How do you experience the co-design process with community, right? With people who have never maybe experienced this type of technology and this type of design process, and how do staff members experience it?
Obviously the co-design process is guided to some extent. So not all of the design questions are necessarily co-designed, but rather we are sort of placing options and also creating a condition by which the people who are interacting with these spaces have an understanding of what are all of the benefits or what is the innovation that they are dealing with. No? So there's a learning process, an understanding, I guess, a metabolizing process, and then a negotiation process between experts, so obviously people who have understanding, and the users of the space. I have to say, these two spaces that we did the co-design process with are collective spaces, so they have a very strong community. In general, that makes a huge difference when you have a community that is highly sort of invested in the outcomes of whatever project you're doing.
Perfect, wonderful. Thank you so much. If there are any further questions, you may ask Matilda maybe during the lunch break. And we are going to proceed to our next presenter, which is Luca Bresegello from the University of Southern Denmark, STU, who will give a lecture on stress-based design for 3D concrete printed horizontal structures. This is addressing the dichotomy of concrete as widely used in the construction industry and highly pollutant. This research introduces a novel approach using 3D concrete printing and stress-based computational design to optimize the use of the material in structural applications. Thank you very much, Luca.
Thank you, Christina, for the introduction, and thank you for having me here. I'm, as you said, Christina, I'm Luca Bresegello. I'm a PhD candidate at CREATE at the University of Southern Denmark, and today I will speak about stress-based design for 3D concrete printed horizontal structures. And CREATE is a research center led by Professor Roberto Naboni, working within computational design and robotic fabrication. And our research interest in 3D concrete printing lies in the in the premise that concrete is, with over 4 megatons a year, the most used material on Earth, just after water. And that in turn, the cement industry causes 7 to 8% of global emissions, with over 1.5 billion tons of CO2 emitted every year. So if we keep doing business as usual, emissions generated by the cement and concrete industry will grow proportionally to the projected growth in population and urbanization. So to reach net zero emissions, a combined effort by all stakeholders is necessary. And of course, a large portion of these emissions should be reduced by rethinking cement composition and its modes of production. However, it is also estimated that over 25% of today's emissions can be cut down through efficiency in design and construction. So finding new ways for carbon efficient design and construction means also rethinking the linear workflow that goes from design to engineering and to construction. And 3D printing, of course, brings geometric freedom and allows to place material only where needed. However, for an efficient material and carbon design and construction using 3D printing, we must consider the tight interdependencies between geometry, material, and fabrication. So our work goes in the direction of developing an integrated workflow that is able to account for these different aspects and integrate and exploit the possibilities given by 3D concrete printing. And our research was pushed forward through experimental work and the realization of a series of incremental structural prototypes of horizontal elements divided in 2 projects. Prior to that, we ran some preliminary process research, and parallelly to the experiments and through the experiments, we also developed digital tools and run fabrication and material tests. So the first phase of our research was to run investigations to achieve a high control over the process, both on the material and on the digital side. All the tests and prototypes were performed mixing a cement-based mortar with admixtures, polypropylene fibers, mainly for cracking, and integrating steel rebars in the structural elements. And all these tests were performed in a robotic setup, which in its final form includes a medium payload industrial robot and a continuous feed mixing pump and a connected silo. And this allowed us to print multiple structural elements in the same printing day with sizes reaching up to 3.6 meters by 2 meters. And this is how the setup at Create Lab looks after printing, so after cleaning up. And in a material perspective, looking at the material performance, we ran 3 different preliminary tests. And firstly, we looked at the compressive strength development of the used mix to understand both the early age behavior but also the stabilization phase and the characteristic strength of the material we were printing with. But a second test series investigated the influence of the anisotropy that characterize 3D concrete printing and 3D printing more in general. So we extracted cylinders in different directions from printed specimens, and we tested them in compression. So the results are highlighting that there is, in fact, an anisotropic behavior in the printed concrete, and that the higher performance is achieved when the specimens are loaded along the layers in the X direction. The third test series was running pull-out tests, so to evaluate the rebar concrete adhesion and the tensile strength in the different printing directions. And besides the Z specimens, so where we casted material and we put the rebar in cast material, the best performing printing direction was the one where we embedded the rebar along the printed layer. So parallelly to material tests, we worked on developing a digital setup, so to be able to design and preview our printed objects. So firstly, with the goal of achieving high resolution control, we looked into how filament width and height could be controlled by changing the motion speed of the robot. And more specifically, we printed and evaluated a matrix of specimens with different layer heights and printing speeds. And from these, we measured the resulting width and as well as the quality of the print. So this provided us with a model we could use to set printing speeds and obtain target filament widths at given heights. So this model was then translated into a digital tool that could provide us with a quick yet reliable preview of the printed object. And parallelly also
it's working again.
Okay, hi again everyone. Can you hear me? Yeah. We are going to start our third session, Mission Meet Reality. I'm the chair of that session. You've heard this morning. My name is Nadja Godiliar-Jamy. This is not working. No.
You can use the mic.
Yeah, but I will need this one for questions. Ah, wait a minute. This should now, this is now working. Okay, then I start again very briefly. We are now about to start our third session, Mission Meets Reality. My name is Nadja Godiliar-Jamy. I'm a postdoctoral fellow at the Digital Design Unit at the TU Darmstadt and a member of the Beam Group. I'm also a co-founder of a French company called X3 who prints large-scale, mostly concrete, for the construction industry. I started X3 in 2015 with a number of other people. I worked there for 5 years as a project manager while I was doing my PhD, and then I decided I wanted to go fully into research, which means I quit the basic daily operations from X3 3 years ago. And when I started figuring out what I was going to say about Mission Meets Reality, I realized how much what I have done now only 3 years ago with X3, what I was involved in the day-to-day, doesn't really make any sense to be shown today because we are much, much further. We are much, much further in the sense that we have seen already quite a few confrontations to the reality of the construction industry in the 2 first sessions. This is something researchers now confront themselves to again and again through industrial partnerships. But what we're about to hear is directly from industrial players, from people that on the daily basis figure out the challenges of putting additive manufacturing into practice for construction. What we are going to see comes from this, and what I'm very happy about in the current session is that we're going to see a lot about not only how additive manufacturing becomes a more reliable process to use in the construction industry, but also how it mixes with other processes. And I'm especially happy to welcome our first speaker, Justin Dierenberger, from Paris, because he has a lot of experience first in pushing additive manufacturing to the industry, but also in confronting it to other processes. Justin is one of the co-founders from X3 as well, but in the meantime, he has moved on to a new venture. He's the Chief Scientific Officer from TETMET, as you can see. He's going to talk about adaptive spatial lattice manufacturing as an alternative to 3D printing, and he's exceptionally well placed to handle the transfer because he is also the associate professor of metallurgy at the Conservatoire National des Arts et Métiers, or CNAM, in Paris. So Justin, please.
Thank you very much, Nadja. Thank you very much to the organizers for inviting me. I'm very glad to be here. I've never been to Formnext before, although I've been working on additive manufacturing for 15 years. So yeah, it's kind of a kid's dream come true. I'm very happy. I'm going to first use my academic cap to talk about architectured materials, which is really what's of interest for me. And in the second time, I will present a way to obtain those architectured materials that is not 3D printing. So yeah, a bit of an abrasive take at Formnext. A short course, a crash course on architectured materials. So I'm a materials engineer by trade. So for me, a material has a function. So we create materials to fulfill a function. For instance, a mechanical function. And if you take this example of a very classical airplane, you have different components, different parts that are loaded in different ways. And if you do your strengths of materials, your design mechanics, you end up with material properties and material property criteria to choose to select the materials you want to use for this part. And those criteria depends on the type of loadings. So this is basic engineering. But this gives us a good way to kind of explore the space of materials. The space of materials that has been mapped using the HB methodology. And basically the idea is to be able to represent material properties as charts like this one, like a 2D chart in this case, with stiffness versus density. And if you do that, you can see that materials fills quite a wide range in this space. But there are some areas, some parts of this space that are empty. Because basically most of those materials, most of those properties depend solely on the chemistry, basically the nature of the materials, their chemical composition, the type of bonds they have between atoms. And they miss one very essential parameter, which is geometry. And so HB, with others, proposed to expand this material space by playing on geometry. So in this case, it would mean to go on the upper left corner, which means very stiff material and very light materials, to have enhanced properties for fulfilling some kind of mechanical function, in this case, making very stiff and very light components. So yeah, to do so, the idea is to introduce geometry within the material and not consider that a material is just, Young's modulus and Poisson ratio that you put in your finite element software, which is usually the mechanical design approach to materials. Because nowadays, and Formnext is a very nice example for that, we have a lot of new advanced manufacturing processes to be able to play with geometry at the scale of the microstructure, at the micrometer scale, at the millimeter scale. So we can actually use all the knowledge we have from structural engineering at the microstructure level. And this is basically what architectured materials are about. So of course, functional performance is not, depending on geometry, is not really a new idea. If you take this example of a bridge, those 4 bridges have exactly the same function, going from point A to point B, but they have very different performance and efficiency. And basically, to finish with HB, he proposed this taxonomy of architectured materials, and as you can see, there's a lot of things that I'm sure you already know, like composite materials and sandwich structures, foams, things like that. And a specific kind of architectured materials, which is lattice-based materials. And in all those structures, the key point is that the overall response of the material is mostly driven by the geometry rather than the chemical composition. And this is especially true for lattice structures. So if you look at the literature of the past, let's say, 20 years, architectured materials have been all the rage. And you can find a lot of paper making a case of architectured materials being the best material ever, the most efficient, the lightest, the strongest, the stiffest. The only problem is that most of these papers, most of these materials, when they are actually produced, which is only a fraction of the literature, of course, let's say less than 5% of the literature, they are produced in labs at for academic purposes. This can take months, 6 months maybe, to make a sample. And of course, there's a big gap to be bridged between the academia and the industry. And as Nadja said before, I like when my research is actually applied in the real world. So just introducing the second part of my talk. So those lattice structures and, as a more general case, architectured materials are the holy grail of material science. They're the best materials you can think of, but they have been studied mostly theoretically. Their impact on the way industry works and on the economy is gigantic. They provide especially high value in aerospace industry, defense, construction also, and which is why you can see those materials. You can see lattice structures in space rockets or in specific buildings. And with StatMet, we finally provided a process to make those materials at an industrial scale, which means for a reasonable price. Yeah. So we have developed this very efficient technology to create lattice structures that we can apply at different scales, from millimeter scale to meter scale. We don't need a 3D printer. You have very nice examples of fully integrated additive manufacturing systems and hall 12 and 11. You know, that will need probably a room of this size to make an industrial scale production of lattice structures. We don't need those expensive metallic powders that are, they are expensive, and that's if you can buy them, because there are a lot of logistics issues there. And also, we don't use voxel-based manufacturing. We are not at a fixed spatial scale. So basically, we have a great process, very flexible, that can save you a lot of material and a lot of energy. And this is 99% less energy than additive manufacturing. So yeah, what is adaptive spatial lattice manufacturing, ASLM, sorry. So it's a kind of additive manufacturing process. It's based on the assembly of metallic or non-metallic wires or rods that are laser cut and welded together with a robot. And this is all supervised by artificial intelligence, of course. Nowadays, everything is supervised by an artificial intelligence. And we are basically building up lattice structures. The process also includes quality control in real time with machine vision. And we end up with optimized lattice-based structures in the end. There are some benefits. So as other additive manufacturing process, there's no waste that is generated. Contrary to most additive manufacturing process, we can use basic materials. Contrary to powder-based additive manufacturing, where most of the energy has to be spent on getting the material that you can actually print. In our case, we can use byproducts of out of the steel factory, if you want, which is just a metallic wire. The process in itself has a really reduced energy consumption, because contrary to wire arc additive manufacturing, we don't have to melt the whole structure. We just have to melt where we need to cut the wire, and we add energy where we need to weld it. So basically at the nodes of the lattice. We don't have supply chain problems because we rely on very common materials, again with very low embodied energy. We have an adaptive spatial resolution in the sense that we can cut the wires to the lengths that we want. So it's very easy to make dense meshes or much more sparse meshes for the lattice. So we can really optimize where we put the matter and how, we can optimize it. This process is enabling large-scale manufacturing of architectural materials. It's robot agnostic, and it's actually being considered for on-orbit manufacturing, which can sound like science fiction, but there's actually ESA project at the moment to do that 5 years from now, with very considerable constraints, like for instance low energy. You cannot do WAM on orbit; it's too energy intensive. You have strong constraints on the materials you can use. Well, that's good for us, etc., etc. And it's a scalable process for industrial application. So basically, we improve the state of the art, which is today topology optimization combined with some kind of additive manufacturing process, for instance, for large structures, WAM. And so our aim is basically to surpass WAM for lattice manufacturing. So this is just a small video because I know you want to see the process. So this is just 2 welding points at R&D speed. And this is done in our offices in Paris, so if you are in Paris, come visit us. Basically, our technology is based on the integration of very simple technologies by themselves, but put together. You know, that's what the difficulty is. That's where the difficulty is. So basically, we use fiber lasers, common industrial robotics, machine vision, beam steering technology, and wire feeding and things like that. So we developed this tool that can be plugged on any 6-axis robot, and of course the software that goes with it. So just some figures about comparison, for instance, for a bracket design or for a bicycle frame. The idea is that we use less material than most conventional process, much less energy, and it costs about the same. Some examples. So I didn't mention, but the company was created in April this year. So 6 months, something like that. This is the first example. This is a nice body-centered cubic cell. If there are metallurgists in the room, you can see that the heat affected zone is very small compared to any other process I mentioned. So this is also good for the mechanical property in the end. Well, this is the same but with 8 cells. This is the same on a plate. Actually, I have the sample if you want to touch it. Just give them back to me in the end, please. There's 2 samples actually. There's a sphere that's not on the pictures that you can play with. And it's stainless steel, so you can go at it. This is some kind of an arch. And yesterday we did this, which is our most complex structure so far, with 283 struts or rods. So we're gaining up in complexity, and the idea is that, of course, in the end we can make lattices of lattices of lattices of lattices. Have almost no weight in the end, and a lot of mechanical properties. So this is the future, right? This is what I'm here for, to tell you what's going to be tomorrow. So hopefully this process can actually be adopted by the industry, and we can create everyday products with this process in a more sustainable way. Talking about sustainability, let's make a car. So this is a lattice car that could be made using this process. This is like an airplane wing. And of course, since we are talking about construction today, truss structures have been used for quite a while in construction. The idea is that we can maybe make it better and faster and cooler. Yeah, there's some other advantages of lattice structures and architectural materials. Through geometry, you can also add function. And this is actually what I've been working for 15 years. You can, of course, play on this weight to mechanical property ratio. You can also control locally the mechanical properties. You can do damping, which is very important for industry. You can play on the Poisson ratio. You can improve acoustic performance. You can make better energy absorption. You can filter frequencies, etc., etc., etc. So yeah, that's our team. We're 7 now, and we'll be hiring very soon. And we don't have architects yet in the team, so if there are architects, looking forward to that. And yeah, just maybe to conclude on this slide, this is a very new process. It's only a few months old. There's no scientific literature on it yet. We are working on it. It's just a new way to process materials, making them more efficient and hopefully add multifunctionality, which again is something I've been guilty of talking about for 15 years, but you can't really see in industrial applications today. We hope that with this process we can actually reach that, and not just oversell a technology to basically redo everything that we know how to do very efficiently with a new technology. So TETMET has been developing this process. It's patented, by the way. Hopefully it's going to be fast, fully automated, and it is frugal in terms of matter and energy. We are also working on a proper life cycle analysis, but our claims are quite well founded, I think. And this is without counting savings that can be done if we improve the properties of the products of our clients. So for instance, right now we are working with the space industry, and of course we can save CO2 on the amount of material and the amount of energy we spend to build the rockets. But if we can save, let's say, 50 kilograms, that's a huge improvement for the whole system. And this is not taking into account with my numbers, so it's actually even more probably. There are applications also in construction, and one of the earlier adopters of this technology is actually Peri, which is a German company. I'm sure you know them. And we've been involved with them recently. And also some more traditional, let's say, risk takers in terms of processing technology like Ariane Group or Airbus. And yeah, that's about it. So if you want to work with us, you can just click this link, take a picture, and we'll be happy to get back to you. Thank you very much.
Thank you, Justin. Are there any questions from the audience?
Thank you for this nice presentation. I was wondering whether there's also a new design tool necessary to create this kind of things. Are you working on that as well?
Yes. So our idea, since we are aiming for the industry, is actually to work with CAD software providers that already have the knowledge, that have lattices integrated in their software already. But of course, they've been developing all that for 10 years for additive manufacturing, which means gradients and nice shapes and all that. We have just straight lines, so it's actually both more difficult in the sense that the current tools are not adapted, but it's actually simple from our viewpoint because the geometry is very simple in our cases. So yeah, we are working on that, but we are counting a lot on our partners to co-develop that. And I'm meeting some of them this afternoon at Formnext.
Thank you. Are there any other questions? Yes?
Yeah.
My question is, right now we saw the example with this cube structure, so wouldn't it be, maybe it's a bit naive my question, wouldn't it be smarter to just say, okay, I create like bends in the corners instead of melting all the corners? Because for me, what I saw was just welds in all the four corners of the cube. And if there are some of the points where you could just bend the wire instead of cutting it and then re-weld it. I don't know.
I'm not sure I understand the question.
So we have the cube, and we have some of the connection points where you have like a straight 90-degree bend, for example. So wouldn't it be like possible to just say, okay, I take the wire, I bend it, and I only cut and
for sure.
weld it?
Yeah. It's okay. It's nowadays. I mean, this is again. We started in April with nothing. It's of course we can consider bent wires. It's it would have to be integrated in the whole tool chain, but it's not there's no technical limitation to do that. The thing is, right now the parts we are working on are structural components that need to be very stiff. And if to start with you have bending in your struts, it will be less stiff than a straight bar, just because of bending stiffness is lower than
Yeah,
compressive
I was
stiffness.
asking about like the corner connections, where you just say, okay, if I have a 90-degree bend and I weld one to it, I have like a 3-point corner instead of welding 3 times for the three studs.
Ah, okay, yeah. Yeah, it's possible. It's actually I mean, your question is very interesting because it's a real problem to put all those struts together. I mean, 2 struts is easy, but we can go up. We have been going up to 32 number of connectivity, so 32 struts in one point. It's a real challenge to do that.
Thank you. Are there other questions?
You might have answered it already with the first question about the software, but with additive manufacturing, we have slicing software that kind of tells the laser what to print at every line.
Yeah.
Do you have your own software to know which rods to put first?
Yeah. Yeah, so we have those building strategies like you have in additive manufacturing, except that in our case it's not like a tool trajectory in a plane. In our case, it's really a vectorized space with. We have a model of all the rods in the structure, and then it's just an iterative process with some optimization, of course. Yeah.
Thank you. I have also a question. I was wondering if you could say a little bit more about the construction applications and the scaling of strategies in that case. Is the idea to have a huge more amount of rather small pieces? Is it about scaling up those pieces directly? And my associated question would be, how does it affect sourcing in the construction industry? Because I'm guessing the metal doesn't come from the same places than for aeronautics.
Sure. So I cannot disclose anything about the construction application we have with Perry, but we have ideas about how this could be used. For instance, we could imagine, creating some kind of architecture, the wall with lattice as a structure and then insulation foam, like people have been doing for 3D printing of concrete. We could also use that as a rebar for concrete additive manufacturing. Maybe, I don't know. What I can say is that with all those partners, we have development projects on very specific use cases. And the idea is that those use cases are realistic and that we can do them in a few months. So it's not a building. It's not a building. It's and we haven't thought yet of the scaling of that. But hopefully, with our partners, we will discuss that together. But we also we are developing a technology that's very specific. We have about no knowledge of the construction industry, the real construction industry. So we prefer to be in partnership with experienced actors for that. So, for instance, Perry.
Thank you.
Thank you.
Are there other questions? Yes.
If you have more number of struts coming to a common point, you'll have more number of wells. What effect will it have on the strength of the part?
Of the part or of the lattice node?
Yeah, eventually the part, I believe.
Okay, so then it's a really valid question, and this is the same question. You can ask the same question for metallic structure in general in construction, but the advantage of having such a fine lattice control is that you can have redundancy of nodes. So of course the weld quality is it's our first priority actually, more than anything else I presented. It's if you cannot reach the weld quality of traditional welding, it's not even worth trying, because I agree it will fail at some point. But the good thing is that we have AI to help us in that endeavor, and also we have research project with academic labs, my lab, to work on the metallurgy of the process, and we do have a project currently to make a proper metallurgical study of the welding joints. And of course, if you weld and re-weld a node, you will change the phases in presence, you will change the properties, but so happens in additive manufacturing. So the worst case scenario is that we are as bad as additive manufacturing, and I think we are much better because we have very small heat affected zones. So that's my gut feeling as a metallurgy professor, but this needs actual characterization and confirmation, and we are working on it at the moment.
Thank you very much, Mr.
Thank you.
I think we can all clap. Next speaker is Bruno Knichard.
Should I stop the screen? No. Oh, I broke it again. I will stay away from it. Okay. Thank you so much.
Bruno leads Additive Tectonics, a company that is working on the future of construction by developing a very large range of architectural 3D printing technology. It's an interdisciplinary company that comprises architects, designers, and builders looking at the latest technologies and ecological advancements in additive manufacturing. Bruno is architect and technologist. He co-founded Additive Manufacturing in 2020, and he's going to show you a few of the challenges to consider when scale, sustainability, and costs are an important factor, which is, I believe, pretty much the case in the industry we're looking at.
Thank you. Okay. Let's hope it works. Ah, perfect. Test, yeah. Yeah, hey, I'm Bruno Knichard. I'm founder of Additive Tectonics, which is basically a spin-off of a big 3D printing company called Fit AG. We founded this company in 2020 in the middle of the pandemic, and it was actually quite good because it was kind of like a small enclave, and we could really focus on doing a construction startup in additive manufacturing, yeah. And because we have this big mothership behind us, we basically have a lot of experience in 3D printing. And yeah, we'll explain a bit what the problems are when you try to scale this up and if you try to make it construction relevant. And then also, construction brings in these problems of sustainability that I will talk a bit about it. But one of the big problems that we have is actually that, to do additive manufacturing, you kind of have to work digital. And the construction sector is the second least digitized sector in the world, but we managed to get to be better than agriculture and hunting, which is pretty good. But it still looks pretty grim for us, especially if you want to also work with AI technologies and these kind of things. You kind of have to be digital to start. But in Germany, where we are right now, which is also a big hub for 3D printing, it doesn't look as bad. Like here, we are at least in the green field here. But we have another problem, and that is that the government is not at all digitized. And this brings us also big problems, actually bigger problems than the construction thing. Because we are actually in construction, we are additive manufacturing that goes into construction. And this is quite exciting. So what we do is we work on developing the future of construction, architectural 3D printing, and I hope we all agree that it's at least part of the future of construction. And we do this by actually putting additive manufacturing at the center of process design and product design. I will talk a bit about what that means. So it's not just about the 3D printing part of it. You have to also design the processes before and after to be able to make products. And of course, you have to design the products because an architect right now, a classically trained architect, can't do this. And we do this in an environment that faces big issues. We talked about this a lot, so I will be quite quick. We generate huge amounts of waste. We don't have a lot of people on the construction side, at least in Germany. Like people don't want to really go into this environment anymore. And then when you start to digitize this thing, it becomes complex quite quickly. So methods are lacking to actually bring this complexity from the digital realm into the physical realm. And then also through modernism, we basically ended up with a pretty monotonous way of doing architecture that that hasn't been done in other styles before. So these are the key issues, and we also have to kind of emancipate away from modernism to actually be able to apply these technologies in a correct way. And we at Additive Tectonics, we do it in a co-design cycle. It's kind of something that I caught off in Stuttgart, where I studied under Akim Menges. And so in our team, we are very interdisciplinary, so we see it from, we have the computational engineering, the design, additive manufacturing, but we also develop construction systems, for example, with Autodesk, and also our own material systems and the cybernetics, which in this case means how our machines communicate with each other, what type of silos you need to actually be able to industrially additive manufacture on this scale. And we need to do this because additive manufacturing is super complex. Like if you look at all of the parameters that go into, that you kind of have to control to make a manufactured part, you see that these types of, parameters are very, very tough to handle, especially by only one profession. So this is why we assembled a quite interdisciplinary team, and also pretty young team, because it is kind of a young people's discipline. And you can see that we grew quite a lot. So here you see 14, we're actually a bit more. And I'm super happy to tell you that half of us are actually here. So if you have specific questions for specific topics, I'm happy to also introduce you all of the experts in these fields. Okay, so what are we doing? We actually focus on 4 main topics: metals, concrete, or let's say hydraulic binders, wood. So basically all the big construction materials, and of course automation and computation. I will just start with additive concrete, and then we can talk a bit later about the other things. So additive concrete, for us it started at TU Munich, where the selective cement activation technology was developed. And we had in the lab like a 50 by 50 by 50 kind of SCA printer. And this technology works with mixing aggregates and the binder inside a powder bed, and then you just activate it by basically jetting an activator on this on the particle bed. And the interesting part here is that we can be quite precise. We can be up to millimeter precision, and this is for like concrete or cement manufacturing pretty insane. What was lacking was the size. So we basically teamed up with a construction machine company and scaled up this machine. So our print bed is 10 cubic meters, like 4 meter by 2.5 meter by 1 meter, and it is the first and only type of its, like it's the only machine that exists in the world right now that is that big, that fast, and can print with construction material. Because this is also important, because you have binder jetting technologies, right? But most of them are not made to work with construction materials, and if you then go into the route of getting a permit to build, you need to kind of work with construction materials. And this machine is also super fast. We kind of range between 6 and 9 hours for 10 cubic meters. So I will tell you later on parts what this actually means. But one very important step I learned at TU Munich is that 3D printing basically closes the digital chain. So you can have a completely digital process to make a part and put it into reality without having a big margin of error and a lot of human interference. So this closing the digital chain is quite important if you want to bring your parts from BIM out into reality, or from a computational framework into reality. Okay, so here you see a prototype of a facade system that we developed for a project in Regensburg. And this was supposed to be 3,000 square meters of facade. And it's basically just a fancy shading, and I don't want to talk really about the architecture behind it. I'm just super proud to say that a thing like this you could fabricate in 2.5 hours. And this makes 3D printing suddenly become construction relevant, because you have to calculate the costs up to your machine capacity, and only if you scale it up with speed and size, you're actually able to be a real player in the construction field. But for us, it wasn't really only about the aesthetic possibilities that we have. We also wanted to integrate functions, and we know this from 3D printing, right? volumetric designs, our internal structures that help us kind of steer the function of a construction element. So we wanted to boil it all together to get multifunctional building elements. And there we teamed up with TU Munich, and Dirk Loke was telling a bit about it. I just want to show you the video and talk a bit about it. So it was inspired by Marcel Breuer, who is basically a modernist architect and designer. And we, for the first time, wanted to see if we can really functionally integrate building functions into an element. And you saw that we also analyzed like how the heat is being transported through our elements and how we can actually use these structures inside of the element to gain a benefit, in this case in insulation. You have the solar potential of self-shading and a lot of other interesting principles that can be solved with additive manufacturing, especially also the curvature. And in my opinion, it's the first time that you can really see additive manufacturing being applied like a prefabricated building element that has a certain extra value to it. Yeah, so in a new recent paper, you can actually read on why we chose certain structures. It has to do with also with our depowdering process, because after the print, basically this part gets taken out of the machine in a big box, and then you have to suck out all of the unactivated material, and you use this in the next phase, in the next print. And this unactivated material is in these cells, so we have to get it out. And it was the first time that something this big and this high res was actually printed in concrete, like it's standard Portland concrete. And there you have some problems with baking. The material basically bakes inside, and it's really tough to get out. So we are really working on this, but you see that, in my opinion, it's already very convincing, even though it was our first real prototype that we did in cement, in standard Portland cement. Of course, you could use other binders, but we wanted to have something that's very available, and we wanted to see if we are able to actually build an element that's this size in one go. So this element took 9 hours to print. This has to do with the compressed material, and the water tends to penetrate slower than with other materials. So it's actually our slowest print. Like we could also do this in 6 hours, but with other materials. And you see that in the back, it's reinforced. Yeah, and of course we also did other projects. This is an art project. It's supposed to be a blood cell. And this is just the smallest piece. We actually did a very, I think, 5 times as big piece like this. Like these are the small projects that you kind of have to do to validate your technology. And then there, I don't know if you see where the 3D print is. It's quite hidden. It's these mushrooms. There you also see a bit our facility, how it looks like. The problem is right now that we are facing is that all of them broke. The mushroom broke, the blood cell broke, also the big element broke. And this has to do with microcracks that happen when you unpack these parts. And this we could only know by doing it big. So there are effects that happen, like you have microcracks that make you be able to handle the part, but as soon as it's outside, these microcracks kind of tend to widen and biggen, and then the part fails. So this is the stuff that we kind of right now try to figure out, like really going into projects and see if we are able to realize this project and learn from them and adapt them. Okay, Portland cement, pretty complicated. Wood. So with the last projects, we developed our own printing material, which is kind of expanded glass from bottles that had their life cycle basically extended, because these bottles normally just have 5 cycles and then they are trashed. And we basically use this old glass, and there are companies that make expanded glass out of them, and we tailored the material together with cement to be able to get a 3D printed material out of it, out of basically recycled glass bottles. And Patrick did all of the material tailoring, gathered all of the data that we had to get to actually know if we are able to print such a large element with it. But in this process, we also noticed that we can do a process like this with a lot of different materials. So wood, chippings, brick, sand, limestone, a lot of possibilities. And we were like, wow, this is really something. Like, you can use waste materials, local materials from everywhere and print with them and make real construction elements in speeds that are relevant for construction. But then reality hit again, and we looked at our setup that we developed during COVID. Like, basically you see these brutalist buildings are silos, and they stand on sensors, and you have mixing and material pumping station in the middle, and it's constantly supervised. And if you have to do it like this if you want to do an industrial machine, an industrial setup. But then, once you have it industrialized, it's pretty tough to react on all of these different materials, because your machinery might not be able to like all of the little chippings and different sustainable materials that you want to work with. So we had to focus, and we focused on wood. So what you see here is a material that we call Econit wood. It's a magnesium wood hybrid. Basically, you have beechwood chippings inside, and you bind them by using magnesium oxycement and magnesium chloride. The interesting part here is that you use this binder, this magnesium binder, also as a flammability retardant for wood. Like, in German we call it Sauerkrautplatten. These plates are made of wood, and you use these magnesium binders to actually protect them from fire. So our binder doesn't just bind the wood, it also makes it fireproof. And we are right now elaborating the acoustic properties of them, but it looks pretty good. And the interesting thing is that if we fill the machine with acoustic plates like this, where every plate could be different, a plate like this, 50 by 50 centimeters, 2.5 centimeters thick, would be 40 seconds to fabricate. So suddenly we are in a range where additive manufacturing can be scaled and can be applied to construction. Okay, so technologically it's possible. The problem is that everybody comes to you and says, let's 3D print this, let's 3D print that, let's do an art project, let's do something really crazy. But this is not how you make money. This is not sustainable. So how you can actually bring this power onto the streets is by making products that need additive manufacturing, where you actually develop the whole process from the design to the finished products. Yeah, so we are in the process of doing that. I have to speed up a bit and develop basically these acoustic products. But there's of course a lot of other potentials with this wood, with these wood products that need to be explored. And if you want to do this, if you want to help us making products out of 3D printed wood, we are happy to work with you. Especially because this biomass doesn't need to be beechwood. It can also be something that grows quick, that harvests a lot of CO2 from the atmosphere. Okay, let's talk about metal. I really have to speed up. So an artist group approached us and wanted to do a big altar project, and they wanted to do it in WAM. And we, together with our mother company, we know how to do WAM, and it would have been 5 times the costs that the artists expected. So we came up with a different way and used basically an SLS print and sprayed aluminium around it, did a lot of material tests. And so basically it's an interesting load case where that's kind of made up, but kind of also made so that the structure has a certain aesthetic. And then there you see how we spray the aluminium around it. The aluminium is there to really reinforce it. Like, we calculated the project just with the aluminium skin around it. And then we assembled it by hand. And you see that it's a very complex puzzle, like 60 different pieces, each individual. And there you see the finished part in the church. And it was actually, the Cardinal Marx came and praised it. I don't know what's in English. That was quite interesting. Okay, so the last topic is computation automation. I will just tell you a story through a project. It's again an art project where we do FDM together with an artist called Peter Lang. He is a landscape painter, and he normally paints layered paintings. Like, he makes very straight lines by snipping a string on a surface. So we said we actually do the same thing. You just have to learn how to model. He didn't want to learn how to model, so we made him a VR interface where he could actually paint his layers. And we made a custom setup for a museum where you could color on the go these prints and would basically give in the color code that he decided before in VR. So he was 800 hours in VR, and we printed 800 hours in Hannover. And actually, it's not just a coloring system for us. For us, it's a way to actually make a new material on the fly. Like you could grade a material, you could use 2 different materials. And you see that this is quite big. And for us, it was intense because we printed it live in a museum, which makes you ready for industrial fabrication. Okay, but you see we overheated the material a bit to get an artistic finish. But we worked together with a company to also do it properly, to make products out of it. We know how to color things, so we use our wood material. Like the whole structure that you saw is basically a lignin-based polymer. And we right now develop a range of products for these people that you might know. Yeah, and we are quite excited to kind of go in the range of products. And of course, we want to push architecture, but to do a startup means you kind of have to start selling things on a consistent level. Okay, so we do very interesting stuff. If you're interested to follow us, feel free to scan the code. And yeah, maybe if you have ideas for our new wood material, I would be very excited to work together with experts in the field. And I'm happy to be here. Thank you.
Thank you very much. Are there any questions from the audience? Well, then I get to start with my question. You were talking a little bit about the demonstration that the projects represent. We were talking about pushing architecture. In my experience, it's as much about pushing additive manufacturing into architecture before you can do it the other way around. I was wondering how you look at the projects you work on, how you choose them, how you work on them in that light of kind of using them as demonstrators to push the technology further into the industry.
Yeah, it's a very good question, and it's actually very tough to choose the right project because we also know that we kind of have to stand behind the projects, especially in the beginning. So a lot of projects we don't show, but we still want to do them to test it. So we basically show the stuff that we like, but there are a lot of projects in the drawer where we are not so happy about showing them. But for sure it means getting the right architects to work with you. Architects that know about 3D printing, and there are not so many, especially in the established field. So I'm counting on you guys.
Thank you.
Can you explain me why we saw the same project in the morning in a DFG basic research funded project and in the afternoon in an industrial research?
Yeah, I can explain. So basically this technology comes out of TU Munich, like the SCA technology. The SCA technology was developed at TU Munich, but the machine development and the process development happens in AT. But of course there are very crucial steps to scaling this up that a university has really troubles to research on. And this is where we come in. And a university would not be able to have all of, or for now, I don't know, maybe it changes now with this big funds that are coming into. Yeah, we work together with them to realize the project. We also were part of the papers that are being written and these types of things, because there is a lot of knowledge that you get from scaling it up, and universities tend to start small. Yeah, and we are, I think, more unrigorous, but more, how do you say? Yeah, we just do it, and then we tend to first do it and then check if it worked instead of over academicizing a problem.
Thank you, Bruno.
There's the question about your mushroom failure story. So
won't ever print any more or produce any more mushrooms.
So the mushroom was an art project. Yeah, we think we have a solution, but we first have to test it in small scale, actually. But we noticed these problems by scaling it up, and we will continue with Portland cement. From an academic point of view, it might seem super simple, like a super tiny problem that you can solve. The problem is in an industrial setup, each little problem that you try to solve means a lot of costs, a lot of extra costs. And we are right now not sure if we can sustain the process how it is right now and solve it. So, yeah, a lot has to do with the green state of the Portland cement. Like you print it and then you leave it 4 days in the powder bed, but then you have to unpack it, otherwise it dries and gets cracks from drying. So you have to take it out of the bed in a green state, and this is where the micro cracks happen, we think. So there are ways to solve it. Some have to do with fibers, some have to do with different post-processing methods, but it's 5 different solutions, so we have to check.
Thank you. We will now move on to our next speaker, Lydia Ratois.
Oh no, we have. I don't think we have.
Okay.
Okay, we did.
We will have to be.
We wanted to check when we start, and hopefully sound will.
Lydia is assistant professor at the University of Hong Kong in the Department of Architecture. She holds a degree in robotic fabrication from IAC Barcelona and is thus our third alumni today from IAC. She worked in the Open Thesis Fabrication Program and before that completed master's studies at UAM in Bucharest. She's currently coordinating the year 2 of undergraduate degree in Hong Kong, and she worked on a project investigating material ecology and sustainability in the realm of robotic fabrication. She used to teach at the Royal Danish Academy of Fine Arts, and what she will show us today has a lot to do with craftsmanship, with the integration of additive manufacturing in contexts that are going to be quite different from what we've seen so far. It's not only now a combination of additive manufacturing with other construction technologies, it's with very much traditional construction technologies. And I'm also very happy that Lydia will introduce us to, I think, our first project today in the Asian context, which means we get to travel a little further in the world, I would say. Thank you, Lydia.
Hi everyone. So I don't speak German, but I assume I can. God help us all, because 2 of my projects are in video format. So today I want to talk about the art of compromise, but what I mean by this is not compromise in the sense of meeting things halfway. To me, the reality of building and of working with novel technology is mostly about bridging between what you conceptually think you want and then addressing local issues within their own context. And I think that's a very important lesson, especially when you build for real humans or non-humans that have very specific needs. This is a project in mainland China that I'm not going to start with it, actually I'm going to end with it, but is a project that my expectations of what I imagine it will be, building in a village in China, and what was the reality of bringing a robot there and building were very different. And I think it's very important to always approach projects with an open mind. I personally never know what a project is going to be when I start it. Rather, I prefer to go there and learn from the sites and from everything that is on the sites. Because I think when you don't do that, when you go in projects with a preconceived notion, you end up with very naive interpretations of projects. This is an Arch Daily comment from someone I think is maybe my biggest fan. But I think this kind of what people maybe think is brutal honesty is very good, because it helps you understand how far the reality is from what we think that a good project is that has to tick boxes. I have to use sustainable materials, I have to do this and that. But actually, I think a good project is about who is involved in it and how it is built, and how do you connect with everything that is on site, everything that is local, how your project is used after it's finished, and if it's a renovation in this case, how you create a connection between the past, the present, and the future, and what's your take on speculating what this future is. And of course, the biggest advantage, in my opinion, of technology is that it allows us to work within a world that is overbuilt without having to tear things down, but working upon what we already have. And I want to show a little bit, I'm going to try to give a quick background on how I arrived at these conclusions. So the first project I want to present today is it's not the official title of the project, but today I framed all my projects as houses because all of them house something. So this is a performative coral habitats, but I named it Underwater House, and I was lucky enough to have this as my first ever client. A client from which I learned very much, and I was very humbled. So this project was a collaboration between the Marine Biology Department in Hong Kong University and the Architecture Department. And it was about, after 2018 when there was a very strong typhoon in Hong Kong that damaged about 80% of local coral habitats. So we wanted to create habitats in which we could place little fragments of corals and they could grow together, but the habitat would have a sustainable way of disappearing without damaging underwater conditions. So we had to bridge together the natural component, which is actually always changing. Nature is not something static. Even underwater, the coral species, there's never the same predominant species, they always change. And then we had to mix the machining component that has its own behavior, and then the human component, because this project was a grant from the government, but it was going to be deployed underwater by amateur divers. So we had to make sure that we create a system that is easy enough so that someone untrained to stay underwater in large periods of time can take it underwater and assemble it. So this was kind of the system that we created. Each tile is actually identical, even though with computational design and robotic fabrication, you have a lot of possibility of tailoring geometries. Actually, each tile had to be identical in order to be able to trace the results. So if the tile would have been different, we wouldn't have known as some of them perform better or some of them perform worse, if that's coming from the geometry or from the corals themselves. And we had to do a lot of tests, of course, when you print with clay, which is a material that has its own behavior, that shrinks. There's a lot of calibration to be done, and we had to do a lot of calibration in terms of the tiles are formed out of two layers. The bottom layers, which cannot be solid because Hong Kong has urbanized reef, so there's a lot of sedimentation, so you need to make sure the corals don't get suffocated, so the sediment needs to be able to pass by. And then we had to test different geometries in order to make sure that the corals can grow within the geometries that we created. And this is the coral fragments when we originally deployed them. This is a little bit afterwards. This is after about 6 to 8 months, and this is after a couple of years. And right now, most of the coral fragments have become a coral habitat by themselves, and they don't need the tiles anymore to survive. So the tiles, because they're clay, they're gonna slowly decompose within 3-4 years, and they're not gonna damage underwater condition. Actually, they can be digested by various species that live in the specific water. And happy client, happy designer. And the next project is the Oyster House, which actually is not a finalized project. And it's a project combining 2 materials and 2 sites. These 2 materials and each material has its own form of fabrication. So there's clay printing, and we've created specific tiles that we use as planters, and we have a two-layer wall system. And then we're using casting using oyster shells. And the reason is, as I mentioned, we're working with 2 sites. The first site is the Cheung Chau Island in Hong Kong. It's one of the outskirting islands of Hong Kong. And in Hong Kong, something that I discovered is that actually nature and the built environments don't need to compete. There's various ways in which they can coexist. And sometimes nature overtakes the built one, and sometimes humans adapt to nature, but there's always this meeting of two worlds that's done somewhat peacefully, to say so. And even though we think about Hong Kong as a metropolis full of skyscrapers, actually more than 60% of the city is a natural park. And then it's bringing together another posture of Hong Kong, which is the city is a city revolving around the dinner table. The dinner table is the most important thing. It's a city of eating. But that, of course, comes with its own implication. More than 30% of the waste in Hong Kong is actually coming from food waste. And there's very little strategies of dealing with this. So initially when I discovered this, I was starting to do a lot of tests with my students and seeing if you can use various food waste as a material for 3D printing. I'm not going to get into that part of the work right now. But then I discovered Lau Fau Shan territories. So Lau Fau Shan is an urban village, to say so. So it's neither rural nor urban entirely, but it's a fisherman village in Hong Kong, right at the most northern point of Hong Kong. There's hundreds, if not thousands, of fishermen who harvest oysters every day. And the problem is that the oysters get sold, only the eatable oyster gets sold, and then all the shells are just simply discarded in the village, and they become trash. So even though the oyster shell itself is not an unsustainable material, the fact that it's not discarded properly attracts a lot of issues, such as pests and odor, and attracts even more garbage, basically. This is Lau Fau Shan. And people have kind of naive interpretations of what they could do with the oyster shells. But actually, there used to be a lot of intelligence in working with this natural material. So in Cantonese architecture, for about 600-700 years, oyster shells have been used for their compressive strength and for their insulating properties. And there's a lot of examples of oyster architecture in South China, basically in Cantonese-speaking areas of China. And when I went to sites, another reality that I had to deal with was that to get a building permit in Hong Kong is near to impossible, because there's a lot of impossible regulations, one of which the strongest one is typhoon proofing. So anything that you want to build, you need to get a special permit to have a licensed engineer to attest that your project will sustain even the strongest typhoon. And that actually sometimes can take years to build. So I thought about how I can sneak around this and how I can make my own reality in order to build something on the site. And I discovered this abandoned sheds, and the regulation actually says that as long as you don't go out of the footprint of an original building, you can alter it as much as you want, and you don't change it structurally. So I decided to create a system to keep the original structure of the building intact, and then only work with the envelope of it and the inside of it, and to combine these two techniques, the oyster casting and the 3D printing. I would like to play a video.
Seems like you have to log in with your own account. You have to give us permission to view it because it's on my account.
Okay,
yeah.
I think I already gave permission. Okay,
You have to check your phone.
My phone.
I think that was the best message before.
Okay. I hope I remember my Gmail password.
That's why I didn't want to ask.
The reality of technology is that it's not always convenient.
Now you have to select it here again.
I hope I have nothing too embarrassing. At this point, I'm fully exposed. I know what everyone's thinking. It better be a pretty good film. I hope I won't disappoint. So since there is no sound, I will be an impromptu narrator. I think this is my karmic punishment for trying to be lazy and just show you guys film that were beautifully narrated and had beautiful music. So there's always a price to pay when you're trying to get shortcuts. So this is the site in Hong Kong, the site where we are building. It's a natural park, as I mentioned, in the outskirting islands of Hong Kong. And this is in Laotian territories where there's the fisherman village. These are my lovely students. Since the sound is not working, I think it's a bit underwhelming to just watch it, so I'm going to try to scroll a little bit faster through it. And the whole Laotian territories, basically, it's a whole village where you can find oysters anywhere. There's oysters trash in people's gardens, on the streets, next to the water, everywhere. So we were going with students there, taking the oysters and then bringing them back to university campus and doing the oyster casting, while simultaneously also 3D printing using 6-axis printing and ceramic clay. And we had to use a lot of different ways of transporting this. So we had to be very creative in how we thought about the building process. We couldn't just do everything, pack it, and send it on site because we have to pass through 3 islands in order to reach the site. We harvest the oysters in the northern island of Hong Kong. Then we go on campus, which is the main island in Hong Kong. And then we had to go to another little island. And for the little island, we also had to take 2 different ferries. The big ferry, and then a smaller sampang boats in order to reach our site. So we had to always be very creative in how we transport things, how we manage to break things down and take a lot of people with us, so each of us can take a little part of the project with them. Finding materials locally in this little islands where the site is. So we had to find basically sifus, which are kind of old school type of masters who are working with their crafts, and we had to buy material from them, and we We had to kind of involve them in the process as well. And this is the project is not finished. We're in one-to-one scale prototyping right now. But we did want to test the oyster casting in a 2-meter tall wall and then the 3D printing system. And I think I will just go quickly through the video. And maybe I can yeah, and basically then the plants were also from the same village. We tried to buy the succulent plants that nobody is buying, that they seem like they're dying, because the site is a natural park and it's all about ecological building, harvesting and growing their own food, taking care of stray animals. So we really had to be very respectful of the ethos of the projects. And something that I maybe forgot to mention is that each project that I'm showing today has a different funding scheme. So I think also part of the reality is building is to be creative with the ways in which you find funding for your projects and how you make sure that you still have enough agency, even though you maybe have a financial dominator over you. And the third transportation mode was, of course, biking for the students. Once we didn't have to carry anything heavy anymore, of course. And this brings me to the project that I started with today, Traditional House of the Future. So this project was a collaboration between me and another colleague in Hong Kong University, also in the architecture department. But we came from seemingly very different worlds. So my world was about digital fabrication, robotic fabrication, on-site and off-site fabrication, very little to do with humans actually, and more related to the environment. And my colleague John Lin's work revolves around investigations in rural China, of course building himself, but also by the time when we collaborated on this project, he had just finished writing a book called Asphalt Houses, which followed and investigated how spontaneous builders, untrained or trained in China, are reimagining traditional Chinese houses. And one of the particular interests was in the traditional wooden house, which is actually very easy to take apart and build back together. So there's a lot of these weird, they almost seem like collages between the old and the new, and the way in which people use their own houses. In this truck, that's actually a house that someone is taking with the truck to another village. And you can see there's always this tension between the old and the new, and even though it's very clear which is which, they still find a way to coexist. And this is an example from Shangri-La, where there's a lot of earth architecture and then a lot of these new additions working with steel and glass. This is the house of a local businessman, aka a mobman. He starts his morning in this room, which is the contemporary part of the house. And then by lunch, he moves to this space, which is half traditional, half modern. And he ends his days, his nights, in the most traditional part of the house where he lives with his family. So this was something that was very important to us, to take into consideration how people live and how they use these houses, and to create a mix between the old and the new. To show another video, but I'm prepared to talk on top of this one, so it won't be sort of.
You only have the sound from the mobile in the microphone?
This one is okay without sound.
Yeah?
But
okay.
So the project is located in Guizhou province, which is in southwest mainland China. And it's a government initiative. So the story of the village is actually that slowly the village is getting abandoned. It's a village with traditional wooden houses, and they're getting slowly and slowly abandoned for the neighboring village, in which it's all generic concrete buildings. But people are moving there because they don't have financial incentives to stay in their own village, and because the traditional house doesn't respond to their needs anymore. So we were actually, me and my colleague, we were teaching together at the time in year 2 in Hong Kong University undergraduates. And we did a series of interviews and surveys with our students, with the local villagers, trying to put together a design brief with the local people. And when you're working with villagers, it's not this kind of hippie, romantic idea that we can have of the village. People are very aware of what they need, and we created a design brief together with them. And the most important thing for them was to have modern amenities, and to have an incentive to stay in the village. So the way that the government responded to that was to create this house that they contacted us for. That would create a focal point in the village, a tourist attraction, and what we actually managed to do was, through the building process, to create a financial incentive for the village, because we had almost all participants from the village involved in it. We have the government, then we had trained craftsmen, traditional woodworkers, and untrained villagers. So the villagers were already self-financing themselves. So this is not an official Taobao village. Taobao is a platform similar to Amazon, but there are people who are working for Taobao in it. And they were basically trying to fund themselves to stay in the village. As I mentioned, traditional Chinese wooden houses it's possible to tear them apart and build them back within 1 day. They use no screws, no additional, everything is done through the way that the joinery is done. So we decided to scan the original house and then adapt the 3D printing part to the original house. That meant that we could completely reuse everything that was original. We simply reconditioned it, and some parts of it had to be chopped off, but the house was put together using only the original wood. And there's something very similar in the way that traditional woodworkers and robots work, which is not something that you would expect, but we both, let's say both worlds, do not really require the use of drawings. So the traditional wood craftsmen, they are working based on models. So we had to make small mock-up models and send it to them and discuss with them. And the robot, of course, operates based on code. So even though you may need a geometry, you don't need a drawing. So that was something very interesting to see, how to create a one-to-one scale project, a real house, without having any construction drawings. And it also required a lot of adaptation from both sides. So there was always this continuous loop between us working with the robots and the craftsmen, because the way that traditionally these wooden houses are done is that you create the structure flat on the ground and then you simply erect it. But because we scanned it and then we 3D printed everything in order to account for every little imperfection in the columns and create all these little nooks in the walls in which you can basically insert the original column, they couldn't do that. So they also had to adapt their way of working and create ways of redoing the frames, reworking within the walls that we have created. So there was never an end or a beginning or an end to the construction process. It was always this loop between us. As I mentioned, even untrained villagers were involved in the construction process, not only the ones that helped us assemble the roof and do the roof tiling, but also the ones who were cooking, who were cleaning, who were doing the waterproofing, because
Of course, nothing ever works perfectly according to schedule, so we didn't manage to finish building during the dry season. So part of the house was actually built during the wet season, and we needed a lot of help from the local villagers to waterproof everything. The new addition to the house made it possible to go from a one-story house to a two-story house. The original house was quite tall, but the ground level was only for animals. But people don't grow animals anymore in the village, so we decided to transform ground floor and also, let's say, human space. So we added all these modern amenities that people were mentioning that they need and they don't have, and that's especially for people with children. It's a very big reason why they leave the village. So we created a bathroom, a modern kitchen, a courtyard, a living room, gathering space. Also, we try to take into consideration how all generations live. And it's quite common in this area that houses are multi-generational, so you would need at least 2 free bedrooms because there's usually 2 free generations living in the house. And you need a generous gathering space because that's part of the way in which people live. And also we try to incorporate within the 3D printing, well, there's no plans yet because the project was just finished when we did it, but the curly wall is basically a planting space for them to plant everything that they might need in a little vertical garden, and then to incorporate a stove and all these appliances that they might need within the 3D printed geometry. So that helped us also a lot to maximize the space in the house. And something that we also wanted to do from the beginning was not to try to fully integrate the 2 worlds, but to have it very clear which one is which. Because one of the requirements from the government was that they want for someone coming from the outside in the village to really think about this village as a place of innovation. That was something that the village head was very adamant about, and they were very open about us using cutting-edge technology. So they were very welcoming to the fact that we brought all these robots on site and doing the scanning and the drone filming. We received actually a lot of support, not only from the local government, but from the people themselves. People are very curious about technology, and there's always this interesting mix. We're all very affected by technology, but how often do we actually benefit from it? And we think we benefit from it, but when you actually think about these areas and where basically technology is produced, it's an interesting way to rethink your own relationship and your own expectations out of technology. We can claim it's unsustainable and we can wait for it to fix everything, but I think it's more up to us to mediate this relationship. And with this robot leaving, I will simply add a few more slides and then I'm done. I'm not sure if I'm over time. I'm sorry if I am. Following this project, the next project, and the project is nominated for the Design Awards and the World Architecture Awards, so please send us some good thoughts. And the next project we are working on, and this project is literally just being started, it's the underground house of the future, in which we're working with another traditional Chinese topology, the underground house. The underground houses are in northern China, and right now they're going through something that was not possible to be accounted for, which is climate change. So a lot of the houses are being damaged because it didn't used to be an area with a lot of flooding, and now they are experiencing a lot of flooding because of climate change. But people still use these houses in modern ways. But also the houses that seem like they're being abandoned, they're still occupied. This is a house that the inhabitant his generation has owned this house for the last 500 years, and he is still living there. And this is his current bedroom / living room / kitchen. And we are working now on a project which will create new rooms and new openings towards these rooms perimetrally, and a completely new courtyard system in which to transform the space into something that is called red and white, which is basically dedicated to funerals and weddings, but it's not a public space, it's still owned by the family. They just do everything within the house that they own. Sorry for the bad pictures, they've been sent by the constructor. And we're creating, again, the mix of traditional techniques using traditional brick vaulting techniques and robotic fabrication on site. Thank you.
Thank you. Are there questions from the audience for Lydia? Well, I will keep my breath.
Thank you for such a wonderful presentation, very exciting. I have a question regarding your oyster project, because it wasn't fully clear, like the oysters that you gathered, you used it just for molding, or also mixed it somehow with clay for the printing?
No, it's simply for casting the oyster. It's two separate systems. We did try oyster printing. The problem is that since it's a project for an actual beneficiary, we cannot really risk that much. So we didn't really manage to get on time a good oyster mix that could both be printed and be durable enough. We did get some prints, quite good ones, but in the Hong Kong climate that is very, very humid, and that about 6 months per year it's the wet seasons, we couldn't risk using them on site.
Thank you.
Well, I will ask a question. In all your project, I think the material formulation is probably quite sensitive. You've told us about how the clay in the reefs dissolves in the end. I'm guessing printing in that kind of context with potential humidity and the whole environment changing could also affect the printing. I was wondering how you work with the formulation, what part it plays in your work and how you tackle it.
So for the on-site projects, first of all, it's concrete, it's not clay. So to begin with, the material is much more durable, and there's a special way of treating concretes. We had in the team that was printing, so part of the story of the project is that this project was done during COVID when we could not go to China. So we had another team from Professor Shu Guo from Shenzhen that was printing for us, and within their team they have a material science department that made sure that the house would be able to survive the climate in southern China, southwest China.
Thank you.
But in this case it was not coming from our team.
Okay, then it is time for final speaker. Thank you, Lydia.
Thank you.
So our final speaker is Miriam Schuster, who studied civil engineering at the University of Luxembourg and at TU Darmstadt. She specializes in structural engineer, and she started by working in Luxembourg at Engineering Office Schröder and Associates. She then returned to TU Darmstadt as an associate researcher in 2016. She defended her PhD at the beginning of 2022 and then stayed on at the TU Darmstadt. She currently leads the Glass and Polymer Research Group at the Institute of Structural and Mechanical Design at the TU Darmstadt. So, as you probably guessed from what I just said, she's going to talk about glass and 3D printing. Thank you for being here, Miriam.
Yeah, thank you very much, Nadia. and good afternoon, everybody, and welcome to the very last presentation of this symposium. So my name is Miriam Schuster, and today I'm going to talk about AM glass with a special focus on thinner glass with a higher stiffness. And all the work that I'm going to present today is a joint work with some project partners and the Glass Competence Center. And for the Glass Competence Center, I also want to mention Matthias Seel and Amir Shadeh. Amir is also here today, and he is writing his PhD thesis about the AM glass. So today I'm going to start with the motivation and the potential of AM glass in the built environment. Then I want to give you an example of thinner glass with a higher stiffness. I'm going to present shortly some AM glass technology and the challenges that we have. Then I'm going to talk about some tests that we already conducted on AM glass components, and I will close the presentation with a summary and outlook. So as we have already seen in this exhibition and also in this symposium, some materials are already more frequently used for AM in the built environment. And here we have, for example, steel, concrete, or polymers. And printing glass is neither very new. However, as we see in this picture, it is more used on a smaller scale, like in the optics or in the electronics. When we are looking at the glass in the built environment, then we have a much larger scale. So we use it, for example, as a facade element. And up to date, we can now produce glass sheets with dimension of 3 meters 20 by 20 meters, which is very, very large. So we see that, we are in different dimensions than the AM glass currently is. So, and the aim of our research is to combine all of those three circles, so the additive manufacturing of glass for the built environment. So when we are looking again at the built environment and the glass, we see that the biggest potential is that it is a transparent material, and that's why it is very often used. We primarily use soda lime silicate glass, and it is used as a facade element, as we see in those pictures, but also as a load-bearing structure, as we can, for example, see in the second picture, where we have a stair in an Apple store, and we see that the staircases are made of laminated glass. We have a fall protection, which is also made of glass, and we can even see some beams made out of glass. One trend is to get bigger glass panes to have individual and customized facades. This is, for example, shown in the first picture. This is the Crystal House in Amsterdam, where some glass bricks were used for this facade. And on the right-hand side from this slide, we see two other very customized facades. In the third picture, we see facade elements with an X. Here, molds were used to create this X, and this X had two advantages. The first one is it is a cool design, and the second one, it brings some structural advantages. Because of this X, we have a higher bending stiffness, and because of that, we could reduce the glass thickness. And in this case, it was also possible to use then some point fixings instead of some linear load-bearing conditions. On the right picture, we see another very individual facade. The top of this glass pane is structured, and in fact, we had here at the beginning a glass pane with a thickness of 10 millimeters, and then the structure was created with many facet cuts where the glass was removed up to a thickness of 6 millimeters. So in order to get such individual facades, we have to make a huge effort, and we need a lot of energy or have to remove some material. When we are now talking about the potential, I first want to show an example of a staircase. Here we see again the stairs and the connection to the walls of the stairs, which in fact are some linear bearings. And now we could imagine that this connection of the stair to the wall could be made by AM. So that's one possible application. Another one is to talk about or think about point fixings. So traditional point fixings in the facade are either glued to our glass elements, or we need some holes in at least one of the glass panes, and then we are connecting our point fixing in that hole. And yeah, the disadvantages of those conventional point fixes is that we need a glue, so we have adhesives, and or we are weakening our glass structure with a hole. And we could avoid this by using some AM glass connections. And the first idea of such a connection was already shown at the Glass Tech, where we created a flipped desk. And in this flipped desk, we had at the four corners some AM components. So there were some glass volcanoes printed, and then we placed them on a glass sheet and laminated it together to a laminated glass, and then yeah, just installed it as a flipped desk. Another potential is to reduce the thickness of glass and to stiffen it with some reinforcements. And here I see two applications. The first one is shaping thin sheets, as we could do it in a similar way as shown in this picture. In this picture we see thin metal sheets. These are pictures from a former colleague of us who was doing his PhD about the van of thin metal sheets. And yeah, we could do this or adapt this procedure for thin glass and create very individual designs. Another possible application would be to have simply flat glass as we usually have it in our facade, as for example here, and print some ribs on it in order to increase the bending stiffness. So we want to have the behavior like on this picture, but we want to avoid removing material. Instead, we want to print some extra material on it. So that's the idea. And here we have two advantages. Of course, we can save some resources since we need less material for the same bending stiffness. And we can modify our design of the glass sheet. Here we have one very specific example. So this is a glass plate with the dimensions of 1.50 meters by 1 meter. And we have a linear support at the shorter sides. So the span is 1.50 meters. And in order to fulfill the serviceability limit state according to the German standard, we would require a glass thickness of 9.1 millimeter, which actually is not a standardized thickness for glass, so we would even go for the 10 millimeter thick glass. However, by modifying these glass sheets by only 3 reinforcements with dimensions of 40 millimeter by 10 millimeter, we could reduce the thickness of the glass plate to 6 millimeters, which is huge, since this means that we have a material saving of approximately 30%, which also means that our structure is lighter, which is very advantageous for the transport and also for the installation. Now I want to present some AM technologies. I don't want to go in more detail for the powder and resin processes, since those are limited to smaller scales and we need really large scales in the built environment, which is why I want to show some people or institutions that are dealing with extrusion processes. So here on the left-hand side we have the MIT, and the MIT was the pioneer in printing glass. And on the right-hand side, we have Maple Glass Printer, which is actually one of the companies that is able to print larger objects. Here we have other persons and institutions. So, for example, we have here Micron 3D printer, extrusion print on a plate. We have Ilmenau and the Laserzentrum Hannover. And on the right-hand side, we have the Notre Dame, and the special thing about this last picture is that they are using hollow tubes, which are then printed. Here we have another picture. This is by Nobula. And with this picture, I want to show that for all the extrusion-based technologies, we have in common that we are printing layer by layer. And when we are doing this, then of course we have the interface between the layers, and there are some notches, and those notches can be a weak point, especially for brittle materials as glasses. So what are the challenges? The challenges can be divided into different levels. So the first level would be the printing process itself. Glass has a very high melting temperature of more than 1000 degrees Celsius. So we are dealing with very, very high temperatures, and we need to control this temperature and the viscosity of the glass during the process. And as we already heard during other presentations, there are even more parameters that can be played with, and we need to find the optimal combination of all those parameters to get then a result that we really can use in the built environment. So the second level of challenges is to characterize the result of the AM component. And of course, we want to remain it transparent. And this means that we don't want bubbles, we don't want to have some crystals, and so on. However, we also need a very good mechanical performance. And therefore, we want to avoid that our AM connection is the weakest point. And instead, we want a very homogeneous connection. Another problem is that due to these high temperatures, we have some temperature gradients in our base plate and also in the AM components, and therefore we have some thermal residual stresses, and we need to control them too in order to be able to design with it. There are some further challenges. As I already said, glass is a brittle material, so when we aim to use it, for example, as an overhead glazing or fault protection glazing, we need to fulfill some safety aspects, which means that we probably need to adapt our post-processing processes, which means that the AM modified glass sheet needs to be laminated to another glass, or we need to try to increase the stress by thermal tempering processes. Another problem that was also already talked about today is the upscaling. So until now, we are working on a kind of small scale, but in the built environment, we need very large scales. And of course, then we have, again, the problem with the residual stresses. Here I want to show some examinations that can be done at different levels of the AM process. In the first picture, we see a thermographic picture. So we use a thermographic camera in order to monitor the temperature during the printing process. And when we finish the printing process, then we can use photoelastic measurements in order to check the residual stresses in our printing component. So that's here the second picture. Then we can use CT scans in order to create some 3D models and to check whether there are some density differences in our component or if there are some holes or other imperfections. We can also do some mechanical testing. For example, we can determine the hardness of our sample. So these are the three lower pictures beginning from the left, where we did some indentation tests on a printed wall, which was on a base plate. And here in this graph, we see the hardness on the y-axis, and on the x-axis, we see the position on our printed object, and the black line is the interface of the base plate and the printed wall. And we can see that there is almost no difference here in hardness, which is good, which means that we have almost constant material behavior. We also performed some load-bearing capacity tests. In this case, we have here a shear test. And I want to present this a bit more in detail. So here we had samples. Again, we had a base plate, and on this base plate, a wall was printed, and this printed wall had dimensions of approximately 25 by 6 millimeters and 6 millimeters in height. And this wall was printed with a laser glass deposition process, and this was done by the Laserzentrum Hannover. Then we took those samples and installed them in our testing machine. So the printed wall was linearly supported, and the base plate was pushed downwards. And the test was completed when failure occurred. And here we see the maximum loads during those tests. So we in total tested 10 samples and see that the mean value of this maximum load was about 2.9 kilonewton. And comparing this to a possible application, which would be the staircase, which is held by the consoles on the wall, we see that this AM console needs to be a load from 1.6 kilonewtons, which is lower than the maximum load that we achieved in our tests, which is good. So then we are also able to produce some digital twins of the actually printed samples. Those digital twins can then be used for finite element analysis in order to determine the maximum stresses, for example. And after breakage, we also looked at the fracture mirror in order to check where was the fracture origin. And here, this is very interesting in my opinion. So we expected 3 different failure modes. The first one would be that the crack migrates through the glass plate. The second one, the crack migrates in a crescent shape. And the third mode would be that the crack migrates through the AM glass wall. And actually, in our test, case 3 did not occur yet. So I think we had in those 10 tests that we did, we had a very good connection between the AM wall and the base plate. So I want to summarize. We see different applications of AM glass in the built environment, starting from point fixings or linear bearings, but I think the biggest potential lies in the stiffening of thin glass. I showed the example that, where we could reduce the glass thickness from 9 millimeter to 6 millimeter by only applying 3 reinforcements. And we did some shear tests where none of the samples has broken at the interface of the base plate and the AM wall. Now coming to the outlook, at the Glass Competence Center we are currently building a glass 3D printer who is using the FDM method. And in this printer, we see it here in this picture, we are able to print on a base plate with the measures of 200 times 300 millimeters. This is the first version of a 3D printer. We are already planning the second version, where the aim is to print on a base plate with a size of 500 times 1000 millimeters. However, this is still small, so our vision is to go for very, very large printers, or to be able to print on the largest glass panes that are currently available with 3 meter 20 times 20 meter. Then there's another thing I want to present to you very briefly. I have talked about that the biggest advantage of AM in the glass field could be to print some reinforcements. And instead of printing reinforcements, we are also looking at local deformations of glass and stiffening it in that way. And here I have a sample where the glass was locally deformed, and here we have then a linear reinforcement. And this is even less material, so maybe also a very, very good option in order to reduce the glass stiffness. So that was all from my side. I tried to be quick. I hope it was okay. If you have some question, don't hesitate to ask. If you want to join our AM Glass network, just contact us. Thank you.
Thank you. Are there questions for last speaker of the day in the audience? Well, then I start. In the MNC printing glass was shown all over, especially in the architect and design world, especially because of the light effects we see. I was wondering if you're looking at methods to design. We also see it in the points plates that has a quite high impact on the localized texture of glass. So I was wondering if you have ways of designing the reinforcement, placement, or geometry combined with the potential light or texture effects that it might have on glass.
That's a very nice one. It's a really good idea. We did not think about it yet, but we should, yes. Thank you.
Maybe we can think about it together.
Yeah.
Yes. Well, we have no more. Ah, great. Thanks.
Thank you for the presentation. One question from my side. What's about durability? So what will happen during the time if you use glass as cantilever? Because of its amorph, and will it degrade during the time?
No, not really. So glass has a really good durability. The problem is more when we have glass in combination with polymers, for example, that then we have a creep behavior during time. But I'm not sure if I really get your question, but...
Yes, maybe so it's more about creep during the time.
Yeah, no, normally it's not the problem since the glass transition temperature of glass is very high. It's above 500 degrees Celsius, so we don't have the viscoelastic behavior in the normal temperature range.
Thank you.
You're welcome.
Thank you very much, Miriam. This concludes our third and last session of the day. Thank you very much, everyone, for staying with us until now. Thank you to everyone for, I think, an exceptional edition of BEAM. I will now leave the instigators of BEAM the closing words to Oliver Tessman and Ulrich Knapp.
Okay, the two old guys with grey hair or no hair are here. This morning we started looking at the exhibition, and thanks Nadia and Philip for organizing this exhibition, and we felt like, oh, super. And it was pretty much like harvesting. What kind of interesting things we started with as a student program, which then grew and grew and grew, and now we are like a weird video, the ones sitting at the back and looking at it. I started collecting some bits and pieces, and Oliver's jumping in. And I take a quote of the first title, Challenge of the Large Scale. That's pretty much what we identify. When we started, it was all these small little pieces, unique, freaky people thinking about doing something very special. And now scale is an absolute interesting issue. 2 years ago, we were the ones with the biggest pieces at the exhibition. Now
that's over.
That's over, exactly. That's entirely over. Technology appears hybrid structures, 2.5 3D printing. Maybe the last one from Miriam is the same setting. Acceptance, price and speed came up as something which is super important. Legislation. Building in Vienna or in the Netherlands is different than building in Germany. That's always an issue. And then design appears as also something which is interesting. And now you're supposed to jump in with pragmatism.
Pragmatism. Yeah, maybe before pragmatism, 3D printing is really, it's there, it's a technology, it's not research anymore. And yeah, let me unpack that. there are new forms. You mentioned that injection printing or spatial 3D printing. So I learned today that so far we did 2.5D printing, and spatial printing is coming now. That's the new thing. We have shooting earth bullets as a kind of additive method. That's a new thing. But more interesting is the pragmatism, and I mean that in a very positive sense. We see that things now make the transfer from research into reality. Interestingly, as that was my question to Bruno, it happens within basic research projects where aspects are identified that are worth to scale, and for scaling we need industry. And I think it's great to see these two sectors growing together. The other thing is that we saw a couple of projects where, in a very pragmatic sense, niches or topics were identified that are worth to realize. I enjoyed seeing the work of Andreas Trummer and his team from Graz that maybe said, hey, let's not worry too much about reinforcement. If we print a permanent formwork, we can build parking garage with additive manufacturing, and I think that was very nice to see that that allows you to jump in scale and transfer it into practice. Matilda showed one slide from IX students about architectonic visions, and we saw a lot of facades. We saw buildings integrated into urban contexts, and maybe 10 years ago, 15 years ago, a computational design program would have shown completely different visions that are disconnected from what we are surrounded about. And I think this ambition is also kind of pragmatic vision. We want to get that built, and the Tova house, you showed photographs of that thing and the renderings, and they were very close. And I enjoyed seeing visions and pragmatism and reality really growing together today. So that was fantastic. Mm-hmm. Yeah, that's if we talk about future research questions. Circularity is one thing. So how can we reuse material? How can we come to different materials? How can we make concrete better, but also maybe use eggshells? Biomaterials, we saw research from Copenhagen and the CETA, and to work with completely new materials for construction. We look at the embedded energy, and if we want to do all of that, it became clear as well that we need new digital design tools, because they are currently not made to represent or simulate, for example, the behavior over time of biomaterials. So that's a new research field that I think is very exciting.
I very much appreciate how our brains connect within seconds. Preparation for this was very short and very, very direct. I'm going to close it up. We had a super impressive, super international speakers lineup. Gender-wise, actually quite good as well. I had a talk this morning with a person hosting women in 3D printing. They have a party later today in this environment. We are invited to join. Let's see if we can go there. It's interesting to see that shift when, say, in our generation, male was dominant. It's really shifting. That's something which I appreciate very, very much. There's this exhibition which you have to look at, no question, and I close with really thank you for all the speakers coming from all over the places, having a night flight, which is really...
I think first I should log out of a Google account.
You survived, you want a hug?